the Associate Dean R&D of IIT Bombay. He was awarded the Gold Medal for the Best Paper in Aerospace Engineering Division during his stay at Institution of Engineers in India. Also, he has been instrumental in setting up the Turbo Machinery Research Laboratory at the Department of Aerospace Engineering. Now, handing over to Professor Pradeep.
Excuse me, sir. I think you are
I
muted.
think, Professor Pradeep, your voice is unmute. You have to unmute yourself.
Sorry. Yeah. So I don't see the share link option enabled here. I think you will need to probably project it from your end. Can you do that? If you have the slides, you can. Yeah.
So we have made you the presenter, so it should be available now.
Yeah, but I don't see the share option enabled. So it doesn't matter. I think I'll just go ahead and talk without the slides. That should be fine. So let me first welcome you all. I think you must have heard this several times in the last couple of days during various orientation sessions that have been held. So on behalf of the Dean R&D's office, I extend a very warm welcome to all of you. And I had a couple of slides which sort of gives an overview of this event and also why Enthuse is important for all of you. You probably would realize that a little later as to why this event is important. So one of the reasons why we have been having this event for many years now is the fact that we would like to sort of give you an overview of the kind of research activities that are taken up here in IIT. But as you would understand, in this very short time that you have, probably about a couple of hours or so, it is impossible for us to take you through all the research activities that happen here at IIT Bombay. We have professors working in areas ranging from very basic fundamental sciences to high and cutting edge research as well as futuristic research areas. And also a lot of professors who work on socially relevant areas which are quite important in the Indian context. And all of these are very important areas that need to be, as an institute, I think it's our responsibility to make sure that all these areas are addressed by some or the other faculty members. So there are close to 700 professors in this institute, and today you're going to listen to about 7 of them, and they're going to talk about their respective areas of research. But that's just a highlight of the kind of activities that we take up here at IIT Bombay. And besides this, there are a couple of other important aspects which you will get into probably in the later semesters where our office can help. One of the initiatives that IRCC, that is Industrial Research and Consultancy Center, helps is with student technical projects, which involves student teams from across various departments who can come together and work towards a very interesting, challenging engineering problem. Just an example could be racing cars, or we have underwater vehicles, unmanned aerial vehicles, and so on. There are quite a few projects which students come together from across various departments. And that's a very useful exercise for students to give them an idea about how to work in a team and how to work with colleagues who are from various departments and not just their own. So that's a very important aspect, and we have seen students really enjoying this kind of initiative. We also conduct during Tech Fest, which is our annual technical festival, we do organize a fairly large expo which highlights R&D initiatives happening at IIT Bombay, quite popular among school kids as well as college students from all across the country who come to visit these stalls. And just a couple of more points I just wanted to highlight before I hand over to the speaker. who's going to talk about their work here. Even during this last several months of lockdown and all the negativity around, we've had faculty colleagues in the institute who have worked hard despite all the hardships of lockdown and so on to come up with very innovative solutions to address mitigation of COVID pandemic in terms of developing various technologies which could address these in some sense or the other. Some of these, of course, you can go through our webpage and you will be able to see a link, separate link for COVID technologies, which have been developed at IIT Bombay in the last several months. So I had a few pictures which show how this event has been held in the past. Typically, this is held in the hostels. Last year, we had organized Enthuse in hostel 15 and 16 in the hostel mess. So these are usually held late after dinner around 9:30 when the mess is cleared. And the snapshots basically show a really jam-packed mess with the speakers in the podium there, something that unfortunately is unimaginable, at least for some more time to come. But that's really how we would have liked to conduct Enthuse in a hostel environment, which is kind of informal, allows you to ask questions freely to the speakers and professors and get to know them better. Unfortunately, this is the best we could do, and please do feel free to interact with the speakers through the chat window. And I'm sure the guests, the speakers would be more than happy to address them during their talk. So that's all I had from my side. Once again, let me welcome you all to this institute, and we all look forward to welcoming you to the institute physically very soon, and hopefully in a few months or so, we should be able to see you back in the campus. So thank you very much, and I also thank the organizers of this event, Professor Atul Shrivastava from Mechanical and Professor Pratibha Sharma from Energy Science, as well as all the professors who have agreed to give their talks today to essentially keep you enthused. So thank you very much, and please do stay safe and stay enthused. Thank you.
Thank you, sir. That gave a really exact idea of what actually Enthuse was in the past years. So, carrying forward the event, I'll ask all the students to write their questions in the chat box. We'll address them each professor have given their speech, and don't spam the chat box. So let's start the event. Next we have Professor Leena Vachhani, Systems and Control Engineering Department. Her research interests include planning and control of autonomous vehicles and embedded control systems. She has also been instrumental in developing two laboratories embedded control lab, Avoidance Systems Arms Lab. Handing over to Professor Vachhani.
Thank you so much, Kriti. Am I audible? Am I audible? Kriti, can you confirm?
Yes, ma'am, you are audible. Yes,
Thank you so much.
Yes,
Before I start, I would request Kriti to prompt me for any questions because there's a lot of non-technical chat going on the chat window. And at the same time, while I'm presenting, it will be very difficult for me to look into the chat window. So you can prompt me any moment of time, right? So let me share my window as of now.
Yes, ma'am, we'll address the questions in the end. Yes.
All right. Can you see my presentation, Motion Planning of Autonomous Robots and Embedded Control Systems? Kriti, can you confirm?
Yes, ma'am.
Okay,
Yes,
wonderful.
ma'am.
And I am making it full screen. Now is it available? Can you see the
Yes, ma'am.
first
Yes,
slide?
ma'am.
Wonderful. All right. Welcome students. This particular program of Enthuse is really to create enthusiasm towards the research, as Professor Pradeep mentioned. And his enthusiastic speech itself makes it enthusiastic for us also to speak about our work here. So I am affiliated with Systems and Control Engineering Group, which is an interdisciplinary group. And I do work in the area of motion planning of autonomous robots, as mentioned by Pradeep. So let me talk about some of my work, which involves robots, different kinds of robots, which we have built in our laboratory. The first one out of that is a very interesting piece is Spherical Robot. As you see on the window, so far you have worked upon with the pendulums and so on. So this particular mechanism is also yoke and a pendulum mechanism where the yoke is revolving and is making the robot to move in the forward direction, whereas the pendulum movements make it the imbalance of the mass, so it helps you in the steering and so on. So once you start modeling this particular device, it is highly nonlinear, and a lot of control part is part of it, which I'll not scare you about. But it is very interesting part to look into how it should navigate into the environment, and at the same time there is a camera inside it, and which can look forward for looking into different features and mapping those features. And at the same time, in the autonomous robots, it's a very interesting problem one has to look into is to give the notification about where the robot is moving. Because otherwise it is of not exactly of use unless you are not able to say clearly that where you are with respect to the environment. You can consider that you are moving on a unknown environment, and you find yourself and you're lost somewhere where if you do not know if you do not know your location, or you do not know where you are moving towards. So those problems we do address. The next work is another interesting piece about the autonomous underwater vehicle, which even Professor Pradeep mentioned. This is the AUV team, Autonomous Underwater Vehicle team. Students, about 25 to 30 students, have been working on building up different versions of AUV since about 10 years now. And we have come to a level where you are able to do multiple tasks with the vehicle. So right now you can see this is particularly the competition called RoboSub, and you can see that this vehicle is able to shoot torpedoes within the hole. So what is more important here is to understand from the engineering aspect that one has to look into the vision part of it. One has to look into the stabilization of the robot. For some time at least, the vehicle should be stable. And at the same time, when it is shooting the torpedo, that time also the vehicle has to remain stable. So those control aspects one has to look for. Very interesting, another autonomous task that this vehicle is going to perform now is to find the location of a sound source. And this sound source location is unknown to the vehicle as of now. So this kind of applications is some kind of finding a black box in an ocean when the airplane crashes, and the black box keeps pinging the sound signals for a month or so. And we know that it was very difficult to search into the kilometers, and rather hundreds, thousands of kilometers into the ocean. So robots can be deployed on those lines. So right now you can see that this is where we did with the help of the theoretical aspects applied to this particular problem, one could do it with certainty and gave the guarantees that these particular tasks could be done. So this white color prop downstairs has a sound source. Now vehicle is surfacing up to show that it has found the sound source. The other aspects of the autonomous robots problems that I look very closely are the multi-agent collaborative applications. In these collaborative applications, basically we look into the aspects where you have very small robots and they are doing something in collaboration. Multiple such robots are doing something in collaboration. So at the same time, one has to look into that the robot is capable of doing some kind of sensing and at the same time is able to take its own decisions. So somewhere we are relating to the edge computing complex. So there are multiple such applications we have worked on: exploration and mapping, coverage, coverage of an environment, and trapping the target such that you are doing some kind of encircling of the target. I will only give you some idea about the swarm aggregation problem here. So this swarm aggregation is again motivated by the idea that there are school of fishes in the pond, and once you throw a food particle, these fishes come and collect towards the food particle. Now, what happens here is while moving, fishes may not be communicating with each other, right? So where the food particle is, and they are looking forward for hunting towards that particular food particle. So all that has been modeled, theoretically viable. Control laws have been devised. So what is the advantage with theory is that we could certainly say that even if certain such fishes are outside, certain such agents are perturbed, as in their movements have been changed, still this particular task will be done with certainty. And it will also avoid, without doing anything extra, it will be able to avoid any obstacles within with whatever is coming to in view of it. And so you can also use them to move along a set path also, if the path guidelines are given in some sense. So all that is possible. We didn't do anything extra new for different kinds of environments. What I'm trying to say here is the control law is same. You apply to any kind of such kind of obstacle environment, this particular aggregation will happen. That is something we can say it very guarantee when we relate to the theory aspects of it. Something similar we did for the collision avoidance part here. Okay, I don't know. Just give me a minute. I think it will finish up and then only I'll be able to. Okay, so this is what is another interesting piece of work, which is doing the collision avoidance of multiple robots. Now, what is important here is to do such decisions at individual robot level. So what is the interval available where the robot can take the decisions? Those decisions have been taken in a digital computing way, such that the entire computing is done either using adders, shifters, like in the digital computing way, multiplication or division by 2, right? So that is also going to give us a very much important aspect of it, such that we are able to do at a digital processing level these decisions, these intervals, identifying these intervals. It is not requiring too much of computations and so on. So one can do this collision avoidance on a single chip itself. You don't need to worry about too many heavy computations here. So moving forward, we looked into certain aspects of Android apps development, because now almost everything, all sensor pack is available at the with the smartphone. So why not to use the smartphones sitting on the robot? So that the robot development part, all these algorithms that I discussed can be just plug and play for you. Yeah. So that is what we are looking forward for open sourcing as well. The last part I would like to introduce, rather I'm introducing to the student community for the any community in the IIT Bombay for the first time, what is the aspects of the newly developed center called Technology Innovation Hub. We'll be working on the technologies for IoT and IoE. From the student point of view, what is more important is that this hub is going to give a lot of multidisciplinary aspect to the technologies. And there's going to be opportunities for internships, of course, with the help of the faculty members, which will be directly involving the industry problems to work on. That's it for my side. I hope I could generate some interest. Yeah. So over to Kriti. Yeah, Kriti, could you see any technical questions that I would like? I'm happy to answer. Or maybe Atul can help me out.
Yes, indeed. That
Yeah,
was really interesting. Even I got caught up. So, Sahil Vaidya has asked a question. He has asked, does AUV has sonar sensor? If
Yes.
yes, how much it costs?
Yeah. So we have not yet procured sonar. Sonars are really costly equipments. So we have been doing collision avoidance without sonar so far. That is very interesting to look at those aspects using the vision part of it itself, uh, because there's not much of accuracy required in the AUV underwater domain. uh, Obstacles are not very cluttered, as in when you go underwater, deeper into the water and so on. Most of it is rather the problem is more to deal with free space, memory requirements, how to see which part is free and which part is occupied, and so on. So the collision avoidance for the underwater domain is not so much important here. But of course, from the robotic competition point of view, it was very much important. But students are still able to manage it with just vision cameras. I mean, vision inputs. I hope I'm able to give some. So that is where another the aspect comes in. When you are constrained with certain sensors, how would you are still be able to answer to a certain level of work? Yeah. Yes, Sahil. Thank you for the
That
question.
answers the question. Yeah, that answers the question really nicely. So, has asked a question like, what about hybrid system? Are we making our machines energy conservative? If not so, then why not?
Of course, one has to look into the endurance of these robots, and one has to be always be aware about what is the processing being done, and that's the reason when we do things with the embedded processing, one has to be very careful on looking into control laws or the sensor processing and so on, which are limited and which are not energy consuming. Yeah, so one has to be I mean, when you are looking into multiple such aspects of the robot design, which involves multiple disciplines, energy is a part of it. Yes. One has to look into the endurance, because finally that is giving you the answer of how long your robot is able to travel, how long your robot is I mean, it requires how frequent chargings and so on. Hybrid approaches are being hybrid in terms of the renewable energy resources and so on. That's being a part of it also, is always encouraged.
Thank you, ma'am. Yeah, that answers the questions. So students are really excited. There are so many questions in the chat box, but due to constraints of time, like we have to stop it.
Yes, and there are
So like,
many more such questions.
let's
Thank you, Kriti. I request students to ping me anytime over email. They can approach me specifically for such things, and the website is also
find
going to
her
give us.
email in her website. Yeah.
Thank you. Thank you.
Thank you, ma'am. Thank you so much. So let's take the event forward, and I see many questions in the chat box regarding how to start research and stuff. So we'll address all those questions in the end. Shruti would give you deeper insights on how to do that. Now you just have to write the questions about the PPTs or the slides that profs are sharing and giving you information about. So let's move forward. Next we have Professor Chandramouli Subramaniam from the chemistry department. His current research interest relates to the understanding of structural property.
Kriti, it is Professor Mahesh from
Yes, sir.
Chemical Engineering Department. It is Professor Mahesh from Chemical Engineering Department. You can see his. I mean, I think you don't. I think you don't have the updated one. The last speaker in this list, Professor Mahesh.
Okay, sir. Okay, sir. Okay.
Yeah, please.
Sorry for the mishap from my part. Next, we have Professor Mahesh from the chemical department. Interests include biotechnology and biosystems engineering, catalysis and reactions engineering, engineering, energy and environment, materials engineering, processes systems engineering, and transport colloids and interface science. Handing over to Prof. Mahesh.
Yeah, hi, good evening. First of all, very sorry for the slip up that was caused by me because I had asked my talk to be advanced today. So I'll just start sharing my slides. Just give me a minute. Okay. So can you see my slides? Is my audio clear? Or
Yes, sir. Yes, sir.
Yeah, Mahesh, it's going great. Please go ahead.
Yeah. Okay. Great. So good evening to all of you. Just a minute, please. There are lots of messages that are coming. I'm sorry. Yeah. Okay. So good evening to all of you. I'm Mahesh Tirumkudulu. I work in the Department of Chemical Engineering, and the areas of my research are in fluid mechanics, colloids, and interfaces. Okay. So today I just want to tell you a simple story about one of the research areas where we are interested in understanding how tiny particles behave at fluid interfaces. Okay. So what I like to do is to start off by showing you an experiment that we were doing in our lab. Okay. So what you see here are in this image to the right hand side at the top, what you see are two wires. These are in fact guitar strings. They're two tiny wires which are separated by a very small distance, by about 4 millimeters or so. And on top of that, we have just placed white colored blades on that. So these are like very thin plastic strips which are kept. Okay. And in between these two blades and the wire, we have a very thin soap film. Okay. This soap film contains particles in it. Okay. And what we wanted to do is to observe what happens to these particles as the liquid dries. So the liquid in this case is water. The particles that we use are plastic particles. These are called as polystyrene, but these are very, very tiny. They are about 3 microns, 5 microns, 10 microns. When I say microns, you know, the width of the human hair is about 80 to 100 microns. So we are talking about somewhere about 1/10 to 1/50th of the human hair. Okay? And these are very, very dilute. So what we have is essentially we have cast a soap film containing these tiny particles between the wires and the blades. And if I were to take a cross section and look at how the film thickness looks like, it would probably look like something like this, where the film would extend from one wire to the other and there would be particles which would be dispersed in it. And the water is simply evaporating. At the bottom, I have a microscope. So what we're interested here is to look at what happens to the particles. Okay, so now I'll show you a movie, what happens when I had 5 microns particles in this. Okay? So as the film starts to dry, we find that the particles start to move, but suddenly there is this very turbulent kind of a motion where particles get plucked, right, as you can see, and they start collecting into a ring. So you can see that a ring is actually forming. You only see a part of a ring because the viewing area is very large and we are only focusing in the central regions. Let me play this movie once again. So these are about 5 microns particles. They are suspended in these thin soap films, more or less transparent, and these particles suddenly move and collect into this band, about a circular band. And so for quite some time I was wondering as to why these particles are moving the way they are moving. Why do they kind of move in and then collect into a band and then slowly start to expand? Okay. So this is the kind of a band one would have seen if, for example, I could see a much larger view of the film. What happens if you take 5 and 10 micron particles and put it in this soap film and start to dry? These are very simple experiments, right? So this is what we find. So in this case, we could see it in the center, but what we find is the larger 10 micron particles first collect, and then they form a ring, and this ring starts expanding, and then the 5 micron particles collect into a ring and then start to expand. It's very fascinating. It appears as if just simply by drying, I'm able to separate a 10 micron particle from a 5 micron particle. So let me play this again, right? So you can see that the 10 micron particles first collect into a ring on this thin soap film, start moving out, and then we have these tinier particles, which are 5 microns, they collect together, and then again they start expanding, so using this very simple method, I'm able to separate the 5 micron particles from the 10 micron particles. Now you might wonder as to why am I interested, or why are we interested in looking at the motion of these tiny particles? Okay. So the presence of particles at fluid interfaces is extremely, extremely important. And one of the places where it's very important is, for example, in ice cream. I do not know how many of you know that an ice cream is almost 50% air, some water, some sugar, and some fat. So essentially, you're paying half the money there for probably the air, because ice creams are 50% air. So what is done in an ice cream is that you take this mixture of water, sugar, and fat, and you beat it. Okay, when you beat it, you produce lots of bubbles in it, right? And then these fat molecules or the globules come and sit on the interface and stabilize these bubbles to give you a foam. So an example here, which is shown on the left-hand side, is actually a foam. And what you have there are these tiny particles which are stabilized, so to speak, by a presence of particles which are present at the interface. And what these particles do is to prevent the bubbles from coming together and coalescing. Okay, so that's why when you eat an ice cream, the texture that you get in your mouth is essentially because of the presence of this foam, which is the ice cream. Similarly, mayonnaise, some of you might have eaten, are essentially oil droplets dispersed in water with these lipoprotein granules sitting at the interfaces, preventing the two oil droplets from coming together. Yeah? In the mining industry, again, it's very important, because when you get the ores, you crush them into fine particles. Some of these ores, you add some chemicals to make them hydrophobic. Then what you do is you pump air at the bottom of it, get tiny bubbles which rise, and these so-called hydrophobic particles, which hate water and have oil-like surfaces, they cling to these bubbles as they rise up, and you are able to separate these bubbles from the mixture. These particles are also responsible for stabilizing these oil spills into fine droplets by sitting at the interface, which leads to a faster degradation by microbes. So it is very, very important to understand how these bubbles or one particular phase is stabilized in other phases. I can see that people already know a lot about these, about sulfidors and so on and so forth. That's great. Yeah. So our general area was to try and understand how does these particles actually behave at interfaces. Okay. So one of the most important, the idea here is what is known as a contact angle. So many of you might already know what a contact angle is. It is essentially the angle made by the interface in the 3-point contact line. Okay. So when you take a water droplet and let's say put it on glass, the glass is water loving. Okay. And so the drop actually spreads, and the angle that the liquid surface makes with the solid surface where it meets is the contact angle. And since water loves to hug the glass surface, those angles are very small. Okay. On the other hand, if you were to take the water droplet and put it on an oily surface, then the droplet of water would kind of ball up. It will not like to spread. So this contact angle is very important when you have one phase in the other phase. So for example, if you have a particle sitting at a single interface and it is water loving, then only part of it will be outside the water So the other phase could be air or oil, and inside one is water. If the angle is 90 degrees, half of it would be in, let's say, air, the other half would be in water. And if it is water heating, so hydrophobic, then much of it would be in air or the oil phase and very little will be in water. So let us say now you have an oil droplet which is dispersed in water and you have these particles. If the particle is water loving, then these particles will go and sit at the interface and stabilize the droplet because much of their area is on the water side. The geometry there allows them to be just protruding a little into the oil side because of the given curvature. On the other hand, if you have it as water in oil, it's exactly the opposite. It is the hydrophobic particles which would stabilize it because much of it will be present in the continuous air or oil phase and a very little would be present at the water phase. I have some equations down here to give some kind of numbers, but what I essentially want to say here is when you have very tiny particles sitting at the interface, it is very, very difficult to remove those particles. So they tend to cling on to the interface because they're able to reduce the energy of the system by coming to the interface. Okay, and therefore the energy required to remove them from the interface is extremely, extremely large. Okay. Okay, so how do these particles stabilize the foams that I showed? So the idea is very simple. For example, if you have a hydrophilic particle, and let us say it is present in a thin liquid film, which is part of the foam, okay? So then in that particular case, what would happen is the particle will not let the film thin, okay, and therefore will retain the film. So it is expected that some hydrophilic particles will tend to stabilize the foam, whereas hydrophobic particles don't like water and they'll pinch off the film and destabilize it. Okay, so people have done these experiments by taking a container, taking water, put some soap in it, and put these particles and just shake them. Okay, you shake them and then you form a foam inside. And then look at the time required for the volume of the foam to reduce from its initial volume to half the volume. Okay. Now you have particles which are sitting at the interfaces in the foam itself. If these particles tend to stabilize the interface, right, then the foam will stay for a very long time. If they destabilize, then it will form. Then the foam will collapse very, very quickly. If they have no effect whatsoever, then the presence or the absence of foam of the particles will not affect the stability of the foam at all. Okay, so what they found is only when the contact angle is close to 90 degrees do they find that it stabilizes the film, which is counter to what has been thought till now, because till now people thought that, well, if the contact angle is very small, that is the particles are water loving, then they should always stabilize the foam. But they find that only close to 90 degrees, which is neither water loving or water heating, do they stabilize the foams. Okay, so we are trying to answer this question by doing that very simple experiment that I showed you right at the beginning. Okay, so let me show you the same experiment now, but with a different technique that we use in the microscope, and that is by using a monochromatic light. It is a light with a single frequency. Okay, and so what we do is we shine this laser light through this film, but because of constructive and destructive interference of light that takes place by reflecting beams from the top and the bottom interfaces, you form these light fringes, interference fringes. And what is very interesting to note, and these fringes can be seen here, you can see there's a dark shade, a white shade, a dark shade, and a white shade, and these are very circular. Ignore these vertical bands, white bands, they are because of a certain technique that we're using. But interestingly, we form these very beautiful interference fringes. And now when you play the movie and you look at the particles, you find the particles come in and then they collect on a particular fringe. You know, all these particles are collecting on this particular fringe, which is moving out. Okay, let me play this again. The particles come in, these are 5 micron particles, they move out and they collect on this nice white circular fringe. Now we know by doing very simple geometry and algebra, you can show that each of these fringes corresponds to a certain thickness of the film. And as the liquid is evaporating, it is thinning everywhere. Okay, and so the particles tend to move along the particular fringe which corresponds to a particular thickness, right? Because of the evaporation, the film is thinning and therefore one particular thickness is moving away from the center, going outward, and therefore particles just follow that particular thickness. Okay, so why is that you see of particles coming in and going out? So what is really happening here is that you have these particles, they have a certain contact angle. As the particles are present and evaporation is taking place, the two particles, the two interfaces come in contact with the interfaces of the particle, and suddenly the upper and the bottom portion of the particle pierces the interface. As soon as it pierces the interface, it finds that the contact angle that is making with the interface is not the equilibrium value. So what one can show by a simple force balance that all of you have done while preparing for JEE, you know that if there is a certain contact angle here, and this is the interface, the interface will have a certain shape that leads to a certain force, and the particle will actually move towards the region where the contact angle will be satisfied. Okay, I know it is very technical. I can see that some of you are commenting that it's too technical for a common person. So let me go to the final conclusion of this. So how does all these relate to what I started off as the motivation? The motivation was that how do these particles actually stabilize the foam or the droplets? And the idea is that the particles will tend to, if the contact angle is close to 90 degrees or so, they tend to move to the regions of the thinnest film and they stabilize it, because it is the thinnest regions of the film which will break. So if you want to maintain a foam, that is, have air on one side, air on the other side, and have a liquid film in the middle which is stable, you want to put your particles in regions which are the thinnest. Okay, and so that is the idea about this whole thing, that you want to tune the particle contact in such a way that you can move it towards the region which are the thinnest. Okay, so with that, I will conclude and I'll be happy to answer your questions. Yeah.
So Sarthak Raj has asked, what is the gamma LV term in the equation?
Yeah, I actually skipped over that.
Area and the contact angle term.
Yeah, so it's interfacial tension between the liquid and the vapor phase. And then someone also asked as to what is KT. K is the Boltzmann constant, T is the temperature. So it's the thermal energy. You will all have studied about Brownian motion. Brownian motion essentially are these molecules which are moving randomly in the liquid. Since these particles are very small, they get knocks, essentially momentum knocks from the molecules which are moving around. And the question one asks is that whether this particular thermal energy, because of the random motion of molecules, can move these particles away from the interface to either of the two phases. And when you do this calculation, you find out that the energy you require to actually move them out is 10 to the power of 7 times the thermal energy at room temperature. So essentially what this is telling you is that particles, once some of these particles sit at the interface, it's very, very difficult to remove them from there. And so they tend to stick to the interface, and that's how they're able to stabilize the emulsions and foams. Yeah.
This is the question. Now, Advait Rishbad has asked a question. In what way does this research improve existing technology?
Sorry? In what way does this? I'm sorry.
Does this research improve existing technology?
Oh, very much. So the thing is, the question is, how do you get a foam to stabilize? Okay, what is the basic principle by which you can make an ice cream, which is a foam which will be stable for a long time? So what should be the size of the particle? What should be the contact angle of the particle? So it's very, very important to understand that. And so it's only by understanding the basic principles as to why something happens in nature can you actually engineer and improve that particular material, or get, by understanding the phenomena, do better things than what is already available in nature. So the idea is that once you understand that, yes, indeed, it is the contact angle which is important, and the fact that the contact angle has to be close to 90 degrees, then you know how to, in fact, increase the stability of these foams.
Yeah, that answers the question. Now, another question. Prapti Sao has asked, what will be the motion when contact angle is zero? Like,
That's a very
what?
good question. So if the contact angle is zero, then the particle is never going to pierce the interface, right? And so what would happen is, that's actually a wonderful question. Who has asked that? Prapti, was a wonderful question that you asked. So, so for example, in this particular case that you see here on the left hand side, I've shown a particle which has just pierced a little bit outside. So if a particle has zero contact angle, then it will never pierce. So as the film thins or dries, the particle will always remain inside the liquid. It will keep moving to the left as you try and thin it. So it will never pierce the interface. It will always be on the water side.
Yeah, very good answer to the very good question. Now, Sanya Arora has asked a question. Why did the two sizes of polystyrene rings form two different layers?
So as I was saying, see what happens is that the two interfaces are actually drying. So the water is drying. So the two interfaces are coming together, right? They're from the top and the bottom. The 10 micron particle is first going to pierce the two interfaces. As soon as it pierces the interface, it moves to a location where the contact angle is satisfied both at the top and the bottom interface. The 5 micron particle is still inside the film because the thickness has not reached that particular point. So wherever it next reaches 5 micron as it is thinning, the 5 micron particle will pierce the interface and then form a ring. And that way, as the film thickness reduces to the point where it can collect the 10 micron particle, it acts like a sieve. It just starts taking the 10 micron with it and starts expanding because the liquid film is thinning. The 5 micron one will thin and then collect the particle and start moving out.
Yeah, I guess that answers the question. Now, there's this last question. Anup Nagdeve has asked this question. That in ice cream, as you said, that it contains only fats and waters, and fats are hydrophobic. Then how it stabilizes the foam?
Very good. So that is the thing. The thing is, the fat, you need the fat because if the fat is hydrophobic, so it comes and sits at the interface. That's exactly the reason. Because you have water, you have fat, these globules, these small flat globules come and sit at the interface because they're hydrophobic, right? And so once they sit at the interface, there's another air bubble which comes right to each other, and one a fat globule sitting at the interface meets the other one and they come in contact, and that kind of freezes the entire structure. So you have lots of these bubbles with fat particles sitting at the interface, and these fat particles prevent the different bubbles from coming together. And that's how you stabilize the entire foam. Very good question.
Yeah. Thank you, sir. Thank you so much. Like students have got many deeper insight into this contact angle and everything. So
thank you very much.
Now I think we should like move forward.
Yes. I'll stop sharing. Yes, thank you. Thank you very much.
I would like to, yes, sir. Next, I would like to call upon Professor C. Subramaniam from the chemistry department. His current research interest relates to the understanding of structure property relations of nanoform of carbon allotropes, graphene, and related doped nanocarbon CNTs. Handing over to Professor Subramaniam.
Yeah, so thank you, Enthuse team. And yeah, I would, is my slides visible now? Can you please confirm whether
Yes, sir, they are visible. Sir, they are visible, but there are some blocks, I guess. The whole slide is not visible. There are some blocks in between.
Blocks. Okay. So is this
Gray
better?
colored box.
Is this okay? If I keep it like this?
Yeah,
No,
it
I guess
seems.
the box are still there, but we can view the slide.
Yeah, Professor, this is Atul. I think there's some bandwidth issue. Can you go to this in presentation mode?
Okay. Yeah.
Yeah, just and let us see if that. Yeah, it is pixelating. Actually, your slides are pixelating,
Oh, okay.
especially in the right towards the right bottom corner.
Okay. So something like this area.
Yes, you're right. Right.
Okay.
Exactly.
I'm not sure. Maybe what I'll do is I'll then switch off my video and
Yeah, let us see if that
would
works.
do. Is this better?
Still, that block is there.
Okay.
Excuse me, sir. Is your WebEx window open on the bottom right corner?
So I've now shared screen. So I'm using there is a pop-up which is coming from the top for the WebEx. Hello.
Yeah.
I just see changing the slide. Just go to the say third slide.
Yeah.
Yeah, that is always there. That block is always there actually.
Oh, okay.
So,
maybe.
but most of the a majority of the part of your slides are visible. So
Okay.
what I would suggest we can continue with this.
Yeah, sure. Okay.
We are not losing much actually.
Okay, fine. Then maybe I'll share this slides with you later, and then you can try to circulate it to the audience.
Sure. Yeah.
Thank you. Actually, thanks for the allowing me to be a part of this Enthuse series of lectures, talks. So I would like to start off with these two famous quotations, which basically defines my attitude towards research. The first thing is, I think, therefore I am, by René Descartes. So this is the Latin version of this, cogito ergo sum, which basically tells you to encourages you to think, and thinking is a process that you have to constantly live with and strive for. Okay. And the second one by Neil Armstrong is research is basically creating new knowledge. So we are in the process of creating new knowledge, and sometimes it leads to applications, sometimes in the immediate future, but sometimes it takes time to evolve into applications. But every bit of new knowledge that is created is a valuable addition to the entire resource of the human civilization. And so that is the basic philosophy that I want you to kind of I recommend approaching research from the basic direction for which research should be approached from. So, like I said, I'm really thankful to the Enthuse team, because I had this opportunity in a couple of years back in 2018, and that actually led to what we got is we were able to make a interactive molecular model in kit with two of the BS students who approached me, Shubham Tiwari and Sanjot Chenoy, and we have actually filed a patent for this. So, and they are right now in their third year. So I think and this molecular modeling kit has, of course, a little bit to do with chemistry, but like you see here, most of it is electronics and circuit level modeling, and that's the kind of interdisciplinary research that IIT is known for, and that is what I would like to project in the next few slides for you. So what we do at our lab is develop new materials, and through that look into the new science of it, try to develop new fundamentals, redefine the existing knowledge, and thereby move towards technology and applications. That basically defines the core of our research activities. So coming to the topic in which I'm going to talk to you about, basically this is a very broad area called nanomaterials. We work on this broad area called nanomaterials. Just to give you an example of how exciting this field is, what you see are blocks of bulk gold. This is golden in color. Of course, it's going to be extremely expensive if you were to buy this gold. And just by the look of it, the color of it, the shine of it, you can tell that it is gold. But now what I do is I take this gold and start breaking it down into pieces. And I make pieces so small that each piece, each particle that I produce is roughly in nanometers in diameter. So this diameter of this particle is roughly of the order of nanometers. Then I see that gold has lost all its shine. Its color has gone. It is no longer yellow in color. In fact, depending on the size of the particle that you make, you can have varying colors, none of which are even closely resembling the beautiful golden color that we see. So these particles of varying shapes or varying sizes can be made, their optical properties can be changed. They can be tuned to go all the way from red to blue, light blue in color. This means that not only is the optical properties changing, the entire set of physical and chemical properties are changing as we, by the very act of taking a big gold, bulk gold, and making it smaller, breaking it into smaller and smaller pieces. And when they approach the nanometer dimension, the properties suddenly start to change. In fact, all of us know that the melting point of a material is a property which is independent of the weight of the material or the size of the material. You take 1 gram of gold, you take 1 kilogram of gold, you take 1 ton of gold. Everything is going to melt at the same point. That is what our knowledge, our textbooks tell us. But suddenly, you see here, as we take the same gold particles, but now the particle diameter is of the order of nanometers. As we approach the nanoscale dimensions, you see that the melting point starts to decrease. And it's not a small variation. It's going all the way from nearly 1000 degrees all the way to about 400 degrees. That means with a normal heater, you can start melting gold, which is impossible to do in case of bulk gold. So there is huge variation in the property. This opens up a completely new dimension because the properties now start to vary as a function of size. So that means we are, even as we speak, entire physical and chemical laws are being rewritten. And this is the exciting, this is what is the most exciting feature of this nanomaterials. So now I would like to start, also give you an open challenge that this is not my own challenge. This was laid down by Sir Richard Feynman in his famous talk in 1960. All of you must have seen this Encyclopedia Britannica. It's about 24 volumes, contains a huge amount of information. But then if you break it down, all the information, it comes to about 500 million alphabets or 500 million letters is what is stored in this entire set of Encyclopedia Britannica, 24 volumes. Now, Sir Richard Feynman, in his talk, challenged the scientific community to squeeze all this information that is carried in 500 million alphabets into the size of a pinhead. Can you do this? If you look at the size of a pinhead, it's about roughly 5 millimeters square in area, less than 10 milligram in weight, and so much in volume. None of these even closely correspond to this 500 million letters that we need to deal with. But the answer is much more simpler. All we need to do is consider the number of atoms that this pinhead has. And suddenly you see that this has about 10 power 17 atoms. So that means we need to code every 10 power 9 atoms for a word. And that suddenly becomes so much more easier and so much more possible to do. And in fact, people have started doing that. Way back in 1990, which is about 20 years back, 2 decades back, people from IBM have actually used and manipulated atoms. Every single atom, what you see here as blue dots, each single blue dot corresponds to an atom. They have manipulated the atom and arranged them in the form of alphabets to write this the logo of their company, which is basically IBM. So we are far closer to reality than what we think we are, and that is all because there is this huge exciting avenue of nanomaterials that has opened up in the last few decades. So coming to my own research, what is happening in this in my lab at IIT Bombay, we are working in this domain called wearable science and technology. Just to give you an idea of where this what is this concept, this photo is actually the first generation computer. It can do amazing speed of 2 to 5 calculations per minute, but it is huge. It occupies almost the size of an auditorium. But now, and this was not so long back, the last few decades, what has happened is your smartphone or your smartwatch is much more powerful than this. It can do millions of calculations per minute. Not only that, it has become small. So this concept of miniaturization of electronic devices and at the same time making it more powerful and versatile is been one of the primary reasons why you are using your smartphone or laptop to such a great extent. It has percolated the society to a huge extent. Now we ask the question in our lab that where is this going to lead to? What is the next big technological jump that can happen? There is no right or wrong answer to that. But what we believe in is we should be able to make devices which are directly integrated onto clothing. That means a shirt tomorrow should be able to do calculations and process data for you. Is that really possible? It looks like science fiction, but believe me, it is already happening as we speak. The biggest problem to this is when we want to think of small portable devices, the immediate question that comes to our mind is, where does the energy come from? We need to provide an energy source to power these devices. And energy for all these devices is required in the form of electrical energy. So where are we going to do that? That means we need to think of energy storage devices. And for that, we go back to our physics, fundamental physics, and define a conventional capacitor. Basically, it consists of two metal sheets sandwiched in an electrolyte, and you can write the capacitance in this formula, standard formula, and you see that capacitance is nothing but the energy that is stored across these two metal sheets, which are separated by an dielectric or an electrolyte. So can we improve this? Automatically, as you see from this equation, the capacitance or the amount of energy that can be stored in the amount of electrical energy that can be stored is a function of area. So that means the area of the interface between the electrode, metal and the electrolyte. So now the simplest trick that we can do is increase the area, make the surface more rough, increase the area, and then suddenly you will see that the dielectric the amount of energy that you can store or the capacitance of the device can increase. It scales up with area. So as you increase the surface area, you can store more and more energy within the same volume of the material of the device. And this brings us to the and you can do a very simple current voltage relationship and try to from that get in a total amount of energy that can be stored. And such devices are called supercapacitors or ultra capacitors because they go one step beyond a capacitor, because they are able to store higher amount of energy purely by changing the surface area of the electrode material. So this is one possibility that we are working on, and this gives us a lot of energy storage possibilities. But then we need to use the right kind of material to with high surface area. So one of the materials that we find interesting is the carbon. The carbon is the allotropes of carbon are very well known. If you go to any standard textbook, it will tell you three main allotropes of carbon are graphite, diamond, and amorphous carbon. But believe me, there are multiple more analogs or allotropes of carbon. Most famous is among them is graphene, which is basically a sheet of sp2 hybridized carbon. If you roll up the graphene, you form carbon nanotube. It's a hollow cylindrical tube of carbons, which is again in the sp2 form. Or if you roll it up in a different way and form balls, then it's called buckyballs. And each of this is a vast area of research. Just to give you an idea, the only one single member of this family, carbon nanotube, can in turn be subdivided into multiple other divisions. So you basically opens up infinite possibilities. So the next time when somebody asks you how many allotropes of carbon are known, the answer is the right answer is infinite number of carbon allotropes. So we work on a very specific form of carbon allotropes called single wall carbon nanotubes, and these exhibit and this is some sample which we grow in the lab. So you can see this, there is a lot of these fibrous material which growing from the substrate. These are all individual single wall carbon nanotubes with a lot of interesting properties. For example, the surface area is about 1000 meters square per gram. So with roughly 1 gram of this material, you can actually cover a tennis court. The strength is 20 times that of steel. People have started thinking about space elevators with this material. Huge thermal conductivity. The thermal transport through this material is very high. And because it's made up of carbon, all this comes at a very low weight cost. It's extremely lightweight, even lighter than aluminum. And it's because it's sp2 hybridized, it's electrically conductive because you have the pi electron density around it. So now with this, what we have done, I'll cut a long story short. What we have done is develop with carbon nanotubes as the base material. We have developed a variety of energy storage devices. This particular photo shows you an energy storage device which is actually integrated on a shirt. A person, like you see, is actually wearing it. It is put on your shirt. And that means you can roll it, you can bend it, you can twist it, you can even hit it with a hammer. Nothing ever happens. And in fact, there is another video which I couldn't share with you. There is you can also hit it. You can also put it in a washing machine and treat it just like any other regular cloth. Nothing happens to this device. So this unit that you see here is actually storing electrical energy, which can be used to power sensors, devices, global positioning systems, or like this video again, which is not playing here, shows you that you can actually power an LED with this. An LED operates at more than 1.8 volts, so you can actually power an LED with the energy that is stored in this kind of a wearable energy storage device. So and the possibilities that we are exploring in our lab are more than that. So I talked to you about wearable electronics here, but we also do a lot of fundamental research related to electrocatalysis. Can we break water into hydrogen and oxygen? And hydrogen being the best source of fuel. We have also used nanomaterials for water purification. We have we have now prototyped water desalination systems which can remove water, salt content from water, the dissolved salt content from water at a very low power cost. And several other sensors for environment and health have been developed in our lab, which I can elaborate on each one of this if you're interested in. But then for the second last few minutes, I want to show you this beautiful looking electron microscope. Think of it like a regular microscope, just that you can zoom down to very close to see very small structures. Just how small structures? These are about 400 to 500 nanometers in dimension. That means it's about 400 into 10 power minus 9 of a meter. That is how big these structures are. And if you see this, it very closely resembles a marigold flower. So we have called this as nanocarbon florets. This is entirely made up of carbons, absolutely entirely made up of carbon in a completely scalable way. We can make it gram scales. So, but what is the use of this? This material, we are trying to see whether this is the blackest black that is possible. When I say blackest black, it might not sound too exciting, but let me show you what it actually can do. This is a piece of paper on which I have used a black marker to make it black. It's a piece of white paper on which I have scratched it with a black marker. Now, if you see, you're still able to see the three-dimensional contours of this material because the material is reflecting light back at you. But the same piece of paper, when I coat it with the nanocarbon florets, looks like this. It's much more black and darker, and in fact, it is very difficult for you to make out the three-dimensional contours. In fact, what you see here, if I don't tell you, you would imagine that this is just a disk, a circle which has been painted with this nanocarbon florets. We actually do this job in our lab. We use different types of paints and processing technologies. But if I just show you the other dimension of this image, you see that this is actually a bowl in which it has been shown, the material has been painted. So you have what is happening is that you are losing the element of 3D visualization because the material does not reflect anything back at you. So you think that it is completely flat disk, whereas in reality it is actually a curved bowl. Similarly, you're not able to make out the undulations of this coated filter paper, mainly because it is a black material that has been coated and that reflects almost nothing. There is no light reflecting back from its surface in order for your mind or a camera to process it. And now we can not only coat it on filter paper, we can coat it on various different substrates, copper sheet, PDMS sheet, different substrates with completely different surface energies. Still the material on which it coats becomes completely black. How do we quantify this? Of course, we take spectra, we record spectra. So you see that the reflectance, we quantify how much of light is reflected from the material. Pure filter paper, because it's white, reflects almost 100% of the light. Whereas the same filter paper, once you coat it with this nanocarbon fluorides or this black powder, reflects almost next to nothing. There is almost zero reflectance over, and what this happens over the entire solar spectrum, stretching from almost 200 nanometers or 250 nanometers all the way to 2500 nanometers. And this is the entire solar spectrum that the sun provides to Earth. So the next question what we ask is, okay, it absorbs the entire amount of energy. It doesn't reflect, so it has to absorb the entire amount of energy. What does it do with all this energy? The answer lies in this. Let me just. I'll take a minute or two. Sorry. At least I'll try to.
Yeah, hi. So if there is an issue in running the movie, if that is the case, then maybe. Yeah. All right. Sure. Please.
Yeah. So just last 2 minutes, I'll finish. So the student is actually keeping the. I'll just go back. What we are doing is we are taking this filter paper which is coated with this black material and putting it under a solar simulator that it simulates exactly what the solar radiation that comes to us from the sun. And you see that within a few seconds, the material is actually started smoking. That means there is an immense amount of heat that is generated on the surface of the material because the material is able to absorb the photons that are hitting it and converting it to heat. It rises the temperature. It rises the temperature to such an extent that if you were to take it with an infrared camera, you see that it's almost 160-degree rise in temperature with nothing but solar radiation. So you're not supplying any other source of energy, just the solar radiation, which we think is freely available to us, is able to generate almost 160 degrees centigrade as a surface temperature. So we use that for water purification, essentially to, again, we generate steam. We take water, create an interface between this material, the nanocarbon fluorides, water, and sunlight. And because of the heat that is generated, the water which is in contact with the carbon material is now nanocarbon is actually converted to steam. The rise in temperature means that water starts evaporating, and then you have a steam generation. In fact, we are able to purify 5 liters of water in just 1 hour. 5 liters is something what you would need for daily sustenance. And you're able to generate, you can do it with saline water, you can do it with turbid water, various different water grades. What you get is pure steam, and once you recondense it back, you can happily drink that water. This is something which is exciting to us recently. So what we have done is we have taken chemical structure. Of course, there's a long story behind it. We have applied nanostructuring, and we have now looked at steam generation. We can also heat up the room, space heating applications, room heating. Like for example, places like Ladakh, which have abundant sunshine but very low temperatures. You can use the sunshine with this material, convert it to heat and heat up the rooms. You can also think of thermochemical reactions. You can think of invisibility cloaks. There are quite a few possibilities that have opened up with this material. So with that, I'd like to thank you for your patient listening. And any questions or any further, if you want to contact me, my email ID is listed and you are free to do so. Thank you. Hope I have not taken too much time.
Thank you, sir. No, sir. Like, there are some questions, so we can ask some question. There is one question. Divij Goyal has asked, can this be basically understood as Tyndall effect property of colloids?
Yeah, so this basic, I think the question is pertaining to this particular slide where I show different colored gold colloids. Yes, it is partly due to Tyndall. There is a lot of scattering that is happening, but this is actually the transmitted light that you see. So if you see the same material in reflection, you will see it in a different color. Does that answer your question?
Yeah, I guess that should answer his question. So let's move on to the next question. This question was asked by Sarthak Raj. He asked that if the technology is small enough to be embedded in clothes, will body heat be enough to power them efficiently?
Absolutely. That's a very, very valid point. That is where we are driving. In fact, that is where technology is driving. Can you use the temperature? Because we are warm bodied animals, irrespective of the outside temperature, our body temperature is trying to maintain as close to normalcy as possible. So, can we use the temperature difference between our skin or the body and the environment and you harvest energy out of it? The temperature difference, like a Peltier effect, if you have read about Peltier effect or Seebeck effect, any temperature difference would, depending on the material, would be able to convert it to a small electrical potential difference. And so that means we can harvest that energy and store it in the form of potential difference, which can be used to kind of charge batteries, or in this case, charge supercapacitors. Yes, that is where we are trying to get.
Okay. This question. There's one last question asked by Pragyesh Gupta.
Yeah.
He asked that how can we manipulate graphene to make spiraling capacitor?
How can you manipulate graphene to make?
Spiraling capacitor.
Supercapacitors. I mean, so see, graphene, by virtue of its large surface area. See, easiest way to think of graphene is you take a textbook, any standard textbook. You imagine that textbook is bulk. Imagine each paper, each sheet of the textbook, that is a planar sheet. Okay, so if you pull out all the sheets, you will get a lot of a lot of very thin sheets. Those sheets, if you do the same with graphite, you take bulk graphite and you start pulling it out sheet by sheet, you get graphene. So essentially, it has a lot of it has got very good electrical conductivity. It has a lot of surface area, and surface area is what is important for making supercapacitors, like you see here. So that people are indeed working towards using it with this graphene to make energy storage devices.
I guess that should answer his question. Thank you, sir. Thank you so much. That gave us a really great insights into the topic.
Yeah,
So
thank you.
I guess we should move forward.
Yeah, if anybody has any further questions, they are free to email me. Thanks a lot.
Yeah, you can get his email ID on his website on Google. So next we have Professor Rajesh Zelek from the Electrical Engineering Department. He is the professor in charge for IIT Bombay Research Park. He also has also served as a he also serves as a board member for SIGN, IIT Bombay Startup Initiative. Before joining IIT, Prof. Rajesh Zele was the director at Max Linear. He also served as the vice president of Mint. Handing over to Prof. Zele.
Yeah, let me share my screen. Okay. Kriti, can you confirm if you're able to see my screen? Okay, all good.
Yes, sir. I'm able to see your screen, but can you just full screen? Yeah, I guess that is good.
I mean, are you seeing like a single window or multiple windows?
I'm seeing a single window, but there are two slides.
Oh, okay, no, then something is wrong. Just 1 second. Let me see. Maybe I'll just keep it like this and show the thing. Okay. Is there some way you can turn off the chat and the sound associated with that?
I think Professor Zele, we can continue. We will try to we'll see if we can turn off the chat,
Okay.
because they are putting their questions over there.
Okay.
And
so
we can, in the meantime, we
so
can.
what I'll do is I'll mute my speakers so that I don't hear the noise.
Right. Because the questions would be taken towards the end only.
Oh, and yeah.
Perfectly
So
fine.
once I start, I think you just have to kind of
Yeah.
shut me down. Yeah. Okay. Okay. Sounds good. Okay. So good evening, everyone. And my name is Rajesh Zelek. The interesting thing I wanted to share with you is that 35 years ago, I was in the same seat that you are in. 35 years ago, I joined IIT Bombay, and then it's been an awesome journey. After graduating from IIT Bombay, I did my PhD at Carnegie Mellon, I have worked in big companies, small companies, startup companies, my own company in India, in US. So I did that for about more than 2 decades. And then 4 years ago, I joined IIT Bombay as a professor. And today I wanted to share with you something interesting that we are doing in our lab. I just wanted to kind of focus on things which are very relevant to India. That's kind of the theme of our lab, which is projects for India. So follow my train of thought, and I will hopefully leave you excited about all these various things we are doing. The first one is a NAVIC receiver. I'll explain you what that is. The second one is a wireless sensor network for air quality. And the third one is a very COVID-related project, so it should be interesting thing for all of you to see. Okay, so let me start with a story for you. During Kargil War, all of you must know GPS. You use GPS in your phones, and during Kargil War, we were denied access to GPS because GPS comes from United States. I mean, they have sent the satellites in the sky, that was something not very desirable. So India has sent its own satellites, which is called IRNSS or NAVIC, navigation satellites for constellation for Indian continent. And so it works in a very similar way as the GPS, but we have our own specifications. So the satellites have been out there for quite some time in the sky, and they've been rotating around Earth. Unfortunately, there is no chip that can decode these signals. And as soon as I joined IIT Bombay, I was kind of volunteered to work on this chip. And in an industry setting, you have like a team of people who are like really pros at it, and then you can develop a chip like this probably in about 10 to 12 months. Unfortunately, I was starting new here, and I didn't have the entire team built up by the time this project came along. So my goal was first to educate the student, build the team, and then develop this chip. And we wanted to develop this chip as something like a professional version, so that we can actually put in the chip inside a cell phone or any other application. So what's going on here is you are receiving these signals from satellite, and these signals are so far away and they are so far down in the noise that you have to have special circuits inside your cell phone or inside a chip to process these signals, and then remove the cut out on the crap and just decipher the signal. And that's what we are supposed to do when we are looking at these navigation signals. So here is the picture of the chip I wanted to show. Really proud of this team. The team on the right you're seeing, we had about 13 students working on this chip, and the square footage of the chip is 2 millimeters by 2 millimeters. And inside that yellow box right here, you see this tiny chip which can decode the Indian satellite signals. Now, when we started the project, we were supposed to do just the Indian satellites, but then, I wanted to put a challenge to the team, and we said, hey, why don't we do a worldwide? So we can decode any satellite for that matter, right? So then the team kind of picked up the challenge, and here is what we have: a chip with 70,000 transistors, which we can decode the Indian satellites as well as the GPS satellites and any other system. Okay, so what's inside the chip, right? So on the left hand side, what you're seeing is a nail, and you can see this tiny chip. This is like the packaged part, we like to call it, and these are the tiny things are gold pads. And a chip like this could be something like maybe, I don't know, $3, $2, something like that, in a large volume. And if you open up this chip, what you will see is a structure like this. And you may, if you're able to see my mouse, the inside red portion is the silicon piece that we have designed. And I'm showing you on the right side is the picture of the chip when we are developing it on the computer. So in the lab, we designed this piece, and then we send it out for fabrication, and this is what you get as a chip, and that gets packaged, and it looks like the one which is on the nail there. Okay, and once the chip is packaged, then you mount it on a PCB, and then you can use it. Okay, so that's kind of the way the whole thing works. I just wanted to give you a feel for how this thing looks like, so that you appreciate it. So this chip is, done by my students who kind of started from scratch. They had no background in this, and I've been teaching classes in this area, chip design area, in electrical engineering. And slowly we built the team over here. We have a lab called ICAS lab, and that's where we do all this cool stuff. The typical industry turnaround time for a chip like this is maybe 1 year. It takes a long time to develop a chip like that, and it takes to send a chip out like this can cost you somewhere north of $1 million. Okay, so it's really important to get everything right, and how you do it is you simulate the chip on the computer and make sure that everything that you do on the chip, there should not be a single error. So having 12 to 13 students, new students, working on a chip, developing their own pieces, and then making sure that there are no errors is quite a feat. It took us 18 months to get this chip out and come back from the fab. And I'm so proud of my team that the chip worked at the first shot. We are able to catch the NAVIC signal. We are able to catch the GPS signal. So it's a pretty exciting project. I just wanted to share it with you. And kind of, these are the kind of things we do in the lab over here. And this is just like a sampler of what we do in terms of chip development inside our lab. There are many other projects which are going on, but I just wanted to show you something that you can touch and feel. Okay. The next project I'm going to talk about is something that's that's probably very close to your heart, specifically people who come from Delhi or some of the highly populated Indian cities which have a lot of pollution. So the project Sattvam is it's all about air pollution, and I don't have to tell you the effects of air pollution. I think all of you saw, due to COVID lockdown, how the air pollution went down, and right after Diwali, you can see the pollution, how it has hit the fans right now, and it's been a problem with a lot of people. So what are we doing in this area, right? So you can there is pollution, and unfortunately there are not that many measuring devices or pollution monitors. There are pollution monitors which are put together by government and some private people, but then there are very few of them. Like in a country like India, you don't have really that many pollution monitors. My dream was I wanted to develop something that's so tiny, so small, so inexpensive, that we can just throw it all over the place, and we can measure pollution as if you're opening your Google map and it will tell you what's the pollution around your area. So we kind of set out to develop this pollution monitoring box in less than 20,000 rupees. A typical pollution monitoring station is crores and crores of rupees. It's extremely expensive. It's very accurate. But what we wanted to develop in the lab was some tiny device which can measure pollution to a reasonable accuracy. I really don't care if I get 1% accuracy, but it's okay if we can get 10-15% accuracy in terms of measuring the pollution. So what we developed in our lab is a Satwam pollution monitoring device, and it's not just a single device, but it's more of a wireless network that we have developed. So, for example, currently we have developed we have deployed this network in IIT Kanpur, where our boxes are scattered throughout the campus, and going to a website you can literally see what the pollution is all over the place. Now, what do you mean by measuring pollution? So there are three key important things that we like to measure. One of them is nitrogen dioxide, then ozone. Also, we would like to measure PM 2.5 and PM 10, and of course temperature and humidity. So we have developed this tiny box that I can show you now, which is the one on the left is our initial prototype from the lab. It kind of looks bulky, right? 1.1, but that's our first shot at it. And we got everything working. And now one on the right, you can see it's a tiny piece of PCB, printed circuit board, which has everything mounted on it. And, we wanted to develop this less than 20,000 rupees and still make profit. So hopefully we will spawn a startup out of our lab so students can develop this and probably make it in a large volume. So pretty cool idea, and it's working very well. And we are able to see we can detect the nitrogen dioxide, ozone concentration, also ppm, the particulate matter concentration in almost like a ppb level. So that's what you need to see when it comes to human health. Okay, so this is our part 2 project for India, pollution monitoring devices and a wireless network of that, which can really give you high resolution measurement over a map or something like that. All right, so here is the last piece of my my talk, which is also very close to my heart. And the idea for this came about during COVID times. What was going on was I have one student who is working as a joint PhD program in Taiwan, and in Taiwan they are able to control COVID in a very well manner. And I've been talking to him, and what he said is that anywhere they go, their temperature is measured. Okay, so the idea that came to me was that, hey, why can't we make a device ourselves in the lab which can measure temperature accurately, and not just accurately, but make it very easy so for people to see it. So what we wanted to develop was a simple box which will measure temperature. So imagine you're going to classroom, right? And at the entrance of the classroom, let's say 4 of you, you're just entering the classroom, and a tiny box there, sitting there, we call it thermomudra. Thermo is thermal, and mudra is a picture image. You see your image there, and it will tell you your temperature. So that's what we wanted to do. Again, you have probably seen something like this when you are at the airport. At the airport, you have this really elaborate device which is measuring your temperature, and that costs a lot of money. And that's something that I cannot deploy in every classroom or every lab to measure the temperature of anybody or everybody coming in the lab, right? So here is what we developed in our lab, and this is the way it looks like. Basically, this is our baby, and this is again the version 1. You can see it's resting on a palm of my student, and if you can see my mouse, here is a visual image camera, and here is a thermal image camera. Now you will quickly see why am I taking a visual image. You will quickly see where I'm going with this, and this is all developed in-house in our lab. We have put together this whole thing, and we have like a first version of it that's already working. And I would like to show it to you. Let's hope that it works. Okay, let's hope that you can see this. So hopefully you can see. These are my students in the lab, and on the left you can see the red colored image, and that's the thermal image. And the right side you can see the visual image. And what this box will do, it runs AI/ML on it, on the data that's coming in. It identifies the faces, and you can see the yellow boxes around the face. Okay, and then it's still under development. It's been about 3 months that we are working on it, and eventually it will also tell you temperature. Right now we can measure spot temperature of each person separately, but through our software we can measure temperature for each individual, and then show you on the screen what the temperature is going to look like for each person. And then hopefully if somebody's temperature is out of line, then we will probably tag that person, and kind of because the key thing about COVID or any kind of contagious diseases is that if you have a temperature, then you probably should not enter a classroom, because we have to assume that every person with a temperature is kind of likely person to spread the disease, right? Okay, so that's kind of what I wanted to show you in a nutshell about the cool projects that we are doing. Again, this is something that I picked out, which will be from a 10,000 feet, will look interesting to you. Really cool stuff going on in electrical engineering. So I just wanted to give you a flavor of it. And if you're more interested in our work going on in our lab, then feel free to just Google search my name in this way, and you will see our website and all the interesting stuff that's going on in the lab. Feel free to connect with the students or me, and would be happy to help you. Again, congratulations to all of you. I'm really looking forward to seeing you on campus, hopefully in near future. And this is where I would like to end my talk. So I'll give you a few minutes to ask me questions, and then we'll go from there. Thank you. Thank you, Pradeep.
Yes. So we can take two. One of the question was asked by Shreya Modi. He asked, "How is Dhruva different from the current GPS receivers?"
Okay, so it's like there are different systems, navigation systems. So our systems, like India's systems, is India's own system. It has its own different frequencies. It has its own secret sauce, so that it's like. Specifically when it comes to military applications, you really don't want anybody else to be looking at your stuff. So that's what is different when it comes to Dhruva. So we have developed this project in conjunction with ISRO, and also there are other people involved in this in terms of helping us with specifications. So hope that answers your question.
Now, we can answer one more question. Asked by Mukul Raj, he asked, "How is thermal mudra different from standard thermal cameras?"
I think you already saw the picture, right? So what thermometer does, I think one of the pieces that I didn't emphasize, and it kind of shows, right? Kind of things we're doing. When you do something for India, then you have to be extremely sensitive for the cost of the solution. So if you try to deploy something like an airport quality solution, then it's extremely expensive. I mean, you're looking at like few lakhs at least to develop a solution like that, something like that. And here we are talking about less than 20,000 rupees. My goal is 10,000 rupees. That's kind of the golden bar that I have set for the team. We are getting there. We are getting close. So what this system does is it's not just thermal imaging, but we also do video imaging. And there are lots of thermal sensors, right, that you can buy on the market and take a picture, but they are not at all accurate. I mean, they will just show you something that's, if something is hot, it will show you with a red color, right? What we are trying to do is detection of human temperature within 0.5 degrees. So that's the different thing we are doing. And we are running a lot of machine learning algorithms in the backside so that we can achieve really good accuracy by measuring. And it gets smarter and smarter. The more reading it takes, it gets smarter because it knows that we have to measure temperature in a certain narrow range and then make a intelligent decision about who's hot and who's cold. So hopefully I answered your question. Any other question?
I guess that answers the question. Yeah, due to time constraint, I guess we have to move forward. Thank you, sir. Thank you so much.
Thank you.
A very insightful
Welcome aboard, everyone. Yes.
presentation. Yeah. So next we have with us Professor Nagamani Jayabi from the Metallurgical Engineering and Materials Department. Her research interests include mechanical behavior of materials, nano indentation and nano or micromechanics, and interface engineering design of damage-tolerant brittle matrix composites. Handing over to Professor Nagamani.
Hello, are you able to hear me?
Yes, ma'am.
And,
Yes,
and
ma'am.
is my
Yes, ma'am.
screen visible fully?
Yes, ma'am.
Yeah, your screen is visible,
You have
Jaya, but would be great if you can make it full screen.
Yes. I'll do that.
Yeah.
I just was wondering if it had the same issue as Professor Subramaniam had.
No, this is perfect actually. Please go ahead.
Okay, all right. Thank you. Yeah, thank you very much to the Enthuse team for organizing this particular event and bringing me on board. And welcome all to the freshman students. Congratulations for getting through IIT Bombay. I would like to highlight some of the research interests that I have had as part of the Department of Metallurgical Engineering and Material Science, in which I have myself joined about 4 years ago. So the group that I sort of lead here is called the Micromechanics of Materials Group, which basically mostly deals with how materials behave under structural loading conditions. And we go through various length scales from nano to micro to macro. So for more information, you will find things about what we exactly do in the website, but I'll try to keep it as simple and general as possible. So why anyway do materials engineering research at all? As we have all read in our maybe history textbooks, human evolution has always been tied to materials engineering in the way we define the ages over the years. We go through Stone Age, then Bronze Age, then Iron Age, and today's is called Silicon Age. So we want stronger, faster, better, quicker, but at very low cost and low weight as well, because we also want to be energy efficient. So there is this process of material selection and design that materials engineers deal with. One is to create new materials and then to select the right materials for the right applications, which is where my main domain is. Because requirements of increased load carrying capability is increasing, we want to, transport more people at a given point of time. We want to transport them faster and so on. So there are lots of boundary conditions and applications, including in terms of temperatures. It could be low or high. It could be mechanical stresses. It could be speeds at which you want to take the component, the number of cycles that it needs to experience. For example, if you think of all the applications where there are cyclic loading involved, including aircrafts, right? There is a pressurization and depressurization that occurs as and when the flight takes off and comes down. So the material has to sustain a number of cycles along with that extreme environments and so on. So this is the domain in which we are testing materials, characterizing materials, and then basically selecting them for the applications. The main problem in all these is to prevent failure, basically because you don't want catastrophe. So the failure can occur under impact or shock loading conditions. It can occur under wear. Wear means like rubbing action that you often see when things come into contact. Fatigue, which is probably what you're experiencing right now over a long event, but hopefully not. But fatigue is a process of failure that occurs at the end of a number of cycles. For example, if you sort of open the paper clip, bend it over and over, it does not break in the first go, but it will break in the 5th or the 6th cycle. So why does material fail under fatigue? Creep usually also talking about high temperature failure, and of course corrosion, which is environmental related failure. So we want to extend life, enhance the reliability and the structural integrity of structures. So various materials have been developed over the years, which help us in achieving these goals, and new materials are coming up with age. And a combination of metals, ceramics, and polymers are used these days. I hope you have an idea at least of this particular classification. So within that domain, you can see various types of composites. For example, hypersonic flight engines, which take up extremely high temperatures and at very high speeds, because you can reach, let's say, from India to the US in 8 minutes or so if you use a hypersonic flight. So what kind of materials are needed to, go at that speed, and the friction and the temperature that these kinds of flights would experience, this is still under development. Similarly, extreme thermomechanical cycling is experienced by aero engine turbine blades. Even in the microelectronic circuits, the solder materials also experience this side of cycling, because there is a temperature increase and decrease that happens as and when we run your devices, like you see your mobile phones or your computers heat up when you use it extensively. Then there are extreme radiations and corrosive atmospheres, extreme vibrations that can occur. So many of these materials are designed to prevent failure and to hold these loads under these kinds of extreme conditions. So the materials tetrahedron talks about the connecting all these 4 sort of features, the structure of the material, the processing, the properties, and ultimately achieving the performance that one would need. And the third, and then sort of the 5th criterion that can come up is the sustainability or the criticality. So I sort of work in the congruence of these domains. So this is our group. The main objective of our group has been to discover materials' mechanical behavior across small length scales. You already saw in Professor Subramaniam's talk that materials at small length scales behave in very different ways compared to the way they behave in macro or bulk length scales. So we are trying to discover, even when a solid is miniaturized into smaller and smaller length scales, they tend to become more ductile or become more stronger. So very strange behaviors are shown by materials at small length scales. So we need to probe at these micron and nanometer length scales, which is what we do, to understand their plasticity and fracture-driven failure mechanisms. So why do we need to understand this? Is because we ultimately want to design damage-tolerant materials with tunable mechanical properties. By tunable, we mean that at various points, we want to achieve different amounts of strengths or ductilities, the ability to extend them more or the ability to hold more loads and so on. This is what our goal is. And I have highlighted these 4 students because these are the BTech students who have been working with me or have worked with me over the past 4 years or so and have done extremely well and have contributed to this group. So I'm actually listing out the contributions of these particular students here. In fact, one of them spent some time making some cool videos about what we do. Hrishikesh Sahasrabudhe, I must credit him. And they also did well during the lockdown, getting some prizes in the contests and conferences and so on. So it's a lot of fun having undergrad students around. And I do hope to see some of you in our groups, and hopefully many of you doing high-ended, cutting-edge research that will help our country. So the tools or the toys that we use in this process is different kinds of mechanical testing units. You can see that the miniature mechanical testing units are just a smaller version of what you see here, which is called as a universal testing machine. Well, you may not have seen this, but this allows you to pull or push or bend specimen. And the same thing at the smaller length scales is allowed in these miniaturized tools. One can put it under what is called as an electron microscope and be able to see what goes on in the material using this combination of in situ probing tool. In situ, by which we mean that we are watching what's happening while it is happening. We also use a combination of finite element modeling to do certain other things, like actually see the stress and strain distributions and predict some of these behaviors even before we sort of deploy the actual material. So I will just want to play the videos if possible. Let me try that. So these are the in situ videos that we recorded while we were testing a material or sample. This has come of age in terms of the automation as well, and you can see that a sample is being pulled in tension, and you can see what exactly is happening and the load displacement response or the stress strain response being recorded during the process. So basically, we're trying to see what is the kind of load that the material can take before it fails, and what kind of failures it can undergo. So for example, it's an extremely brittle material, but the crack does not propagate fully. Why does it not propagate fully, and so on. So for all of these, we use what is called as a nano indentation tool, and we use different kinds of small probes. If you can look at the length scales here, this is about 5 microns, this is about 0.5 microns. So we are testing at really, really small length scales. So why do we need to do this? And what are we planning to achieve with that is basically understanding failure. Like I said, if you take a material like chalk, which is made of calcium carbonate mostly, it breaks in a very brittle manner. You would have all seen this already. But the same constituent material is there in these biological materials called mother of pearl or nacre. Basically seashells that you would have all seen again if you've visited a beach or when you come to Bombay. So you'll find these shells which will not break upon the same kinds of loads that you would apply on a chalk piece. But these are also consisted of 95% calcium carbonate, which is called as aragonite in more scientific terms. But they do have these sort of protein structures between them. So since it's 95% ceramic or oxide, but the rest of it is protein, and somehow this is able to tolerate loads much better than the 100% calcium carbonate structures. So there are various interesting things that can come up with these kinds, but people are studying what the structure is and how different is it compared to a monolithic calcium carbonate material. And they see that the structure, if you zoom into a material like this, is actually like a brick and mortar. Brick and mortar is something that you see in buildings, right? So we have mastered that. The masons have mastered that. So the mortar is the protein and the brick itself is the calcium carbonate crystals. And because of the structure itself, there is a lot of energy that is absorbed by the crack in deflecting, in micro cracking, and so on. And that leads to improved damage tolerance or resistance to crack growth. So this is an example that is shown here. If you have plexiglass, which is just brittle polymer PMMA, also any borosilicate glass, if you put in impact loads, it will break very easily. But the same thing which is templated into a nacre-like structure, the made of the same material entirely, but now into a brick and mortar structure, then it does not break. In fact, it bends quite a lot before it breaks. So these are the kinds of nature-inspired structures or architectures we are trying to make in our lab. So this can be done through what are called as 3D printing processes. Now, something that is probably familiar to you by now, because you would have heard of usage of 3D printing in even making ventilators and so on. So 3D printing is a cutting-edge technology that has helped make structures of various kinds, but also microstructures of various kinds. And where does it help to make these kinds of structures is making bulletproof glasses or bulletproof coverings or window shields. It also helps in making artificial bones if you want to create all these advanced people or people of advanced age. If you want to replace them, their bones with artificial bones, then these are the applications which we are actually looking at. So this is an example of using the same brittle PMMA I was talking about, which is used in various dental applications as well as in many others, and just drilling holes into them. So the the bulk material is now machined such that you have holes of the spherical and the flat kinds, and these just making these micro machined holes has led to an improved damage tolerance in them. Through a process called topology optimization. And that is something that we are looking at in more depth and in detail currently. So it helps to see that these features are able to deflect the crack much more, and therefore the total energy absorbed before the crack grows fully is much higher. Also, there is no catastrophic crack growth, that it does not grow in one shot, unlike what happened in the left side of the figure here. The last application that I want to come to is the cutting tool applications, where what we use are what are called as nitrides. Now, nitrides are also extremely brittle, as you can imagine. These are covalently bonded structures, so they break like chalk. But they are used because they're very hard and wear resistant. And because they're very hard and wear resistant, you would also want to use them in cutting tools and so on to coat them, but with improved damage tolerance. And that can be done through multi-layering with the metal in between it. So this is the TI, TI, and TI sort of a multi-layer. And if you do that multi-layering, we see that improved damage tolerance and improved load carrying capacity is obtained. The red color that's shown here is a 50-layer multi-layer of the same TI, TIN, whereas a 10-layer multi-layer shows a much lower load carrying capacity, and a single layer TIN is breaking at a much lower load. So basically telling that just architecturing helps in improving the fracture toughness and damage tolerance. And this particular system is deposited by what is called as a physical vapor deposition or sputtering tool. And you can see the dimensions here. Each layer is about 80 nanometers in thickness, and you can create an entire solid using this process. So just to end here, there are several opportunities for you to come and do research in our labs. There is this program that is coming up, which is called the Makerspace, which we actually got started with, but unfortunately had to sort of suspend because of the COVID lockdown. There are, of course, summer winter internships, course projects that you can do, and ISERP, which is a program that is run by the Dean R&D's office, which probably will be covered. So these are the fun things that students have done during their first year itself, making raincoats with milk bags. Now, rain is a common phenomena in this particular semester, which you would want to safeguard yourself against, and no better way than to recycle a material, which is a milk bag. And there are lots of things that you will learn when you do things hands-on. So these are the fun things that people who come to the department and come to this institute will experience. Finally, I would like to leave you with this thought process that you have come to an institute. You're now going to be engineers soon, or learning how to engineer, which is basically problem solving. Okay, so ask questions. The difference in solving real life problems is to first ask as many questions as possible. There are no stupid questions. And focus a lot of your time on defining a problem, because there are many potential users who are going to be affected. And if you don't talk to the stakeholders, then you don't have a good idea of what you're planning or what you're trying to solve. Once you do that, do not become or aim to become comfortable ever. Always have that dissatisfaction in life. What I mean by dissatisfaction is that you will never reach perfection, but always aim for making things better and better for yourself and for the society around you. Thank you very much. And I would be happy to answer any questions. I'm sorry if I overshot my time by a lot.
Thank you, ma'am. Now we can go forward to the question session. Tejas Srivastav have asked this question. Is there any way we can use the technology we are using to detect damages to repair them too?
Yes, that's a very good question. There are of late there are lots of research articles you would have seen in what are called as self-repair or self-healing materials. It's not the same technology, but there are materials engineers who are working on crack healing or self-healing processes. Right now, they mostly involve having some sort of a polymer encapsulated, and it sort of comes off when the cracking process occurs, and it comes off and sort of seals the crack. So this is the process that people have been following, but there are also people who are trying to apply field assisted healing of cracks. For example, electric field or magnetic fields. All these field assisted process of sintering and healing of cracks is also something that people are looking at. Yeah. If I don't know if I answered your question.
Thank you. Yeah, I guess that answered his question. So due to time constraint, I guess we have to move forward. So we can take only this much question. Thank you, ma'am. That was a really insightful presentation. Like, gave
Thank you
us
very
many
much.
deeper insight into the topic.
I'm
Yeah.
looking forward to the students
Uh,
coming back soon.
yeah. So next we have Prof. Venkata Santhosh Kumar from the Civil Engineering Department. His research areas include infrastructure project governance, construction project management, organization in projects, and infrastructure sustainability and structural engineering. Handing over to Prof. Venkata.
Okay, good evening. Can you hear me? Okay,
Yes, sir. Yes, sir.
thank you. I hope you can also see my slides.
Yes, sir.
Okay, so good evening, all of you. Warm welcome to IIT Bombay. For the civil engineering students, probably this is the second time I'm welcoming them. We have met briefly during the fresher orientation as well. So today again, I would welcome you back. Ideally, this could have been a very buzzing kind of environment where you all sit in a mess and then we all kind of interact. But this is the the truth of the day, and let's see what we can do here. But hopefully, you will be back on campus soon, and then we would have much more engagement that way. So, coming to my kind of topic. So I'm Venkata Santhosh Kumar. I work in construction technology and management in civil engineering. And particularly today, I want to discuss a few projects which look at AI and ML, artificial intelligence and machine learning approaches to manage construction projects. And I would be particularly talking on these applications to planning and safety. That's the idea right now. So let's start it off. In fact, earlier I've made a presentation to Enthuse in 2018 or 17, if I remember. And then I'm happy to say that some of the students actually started working with me, those who present in Enthuse after, probably first, second year or something. And then many of the applications which I show you as part of this presentation are works from these BTech students. Okay, so that's the theme of this presentation in the next 15 minutes or so. So let's just start off with this whole idea of civil engineering. So whenever we talk about civil engineering, we imagine these large things, right? You imagine probably some of you would be staying at the top corner thing. That's the hostel at one of the hostels at IIT Bombay. But you also look at these large things, bridges, like for example, the band worldly ceiling. But then there are a lot of things which are invisible and which are probably also quite important in terms of civil engineering, right? So, for example, we almost manage the entire transportation infrastructure, construct it, maintain it, and then you have, for example, in the bottom left corner, we are the ones who take care of water resources. Not only that, we also take care of how to manage your wastewater, solid waste management. So there are invisible functions, there are quite visible functions, as you can see, which civil engineering is all about. So you have a wide variety, a plethora of applications which you actually have when it comes to civil engineering. And as I say, we go from micro or nano scales to so you go from a nanoscale to a macro scale when as far as civil engineering applications are concerned, right? So let me just give you a small idea of what some of the research at IIT Bombay Civil Engineering Department does. This is probably about 1 or 2% of what's happening. I'll just give you a flavor of the wide variety of research which is happening. Okay, so for example, if you are wondering what you can do as part of civil engineering, because we are building structures from last few thousand years, and what's more we can do. So this is what some of you can start doing, right? If you want to play with cool gadgets, so this is driving simulator at at the Transportation Systems Laboratory at IIT Bombay, and you can actually simulate the actual driver behavior. right? So what you see on that screen is essentially someone who's driving a car and also using his mobile phone, right? And then you introduce randomly certain obstacles, right? A traffic light turning red, or a speed breaker which is coming up, or probably a cow on the road, a pedestrian on the road, and you want to understand how this driver is going to behave, what's kind of reaction time, etc. And you actually have facilities to simulate that. So that's one thing, which you can do. The other thing what you do is, this is one of the facilities which is coming up. So this is what we call the virtual cube environment, or what we call IVRS at IIT Bombay. We are in the process of building this, where you can transport the entire individual virtually into a construction environment, right? So there you can actually simulate, for example, one-off construction events, right? For example, you have an underwater repair which you have to carry out, and there is only a single shot at which you can do it. Then you can actually simulate the entire construction sequence in this kind of cube environment and understand that what are some of the things which can go wrong and probably rectify them, right? So that's something which you can do, right? Then you can go very nano scale, right? You can go micro scales. For example, this is the structural, this is the electron microscope image of how concrete looks under a microscope, right? So the important application is, this beautiful structure which you see there on the micro scale. By looking at it and understanding the matrix of, the material, how it is bonded, etc., what you can do is you can design the applications where it can use. So if you, for example, if you want a very high strength concrete, right, which can be used for example, the bullet trains which pass on, or if you want to kind of create a very dense matrix of concrete which can probably resist your projectiles, like a speeding bullet, or for example, a blast resistant structure. Like for example, if you want to design a column in a terminal building of an airport, which should function even in case of a blast event. So those are the kinds of applications which you can develop by looking at the material perspective. So that is something which you can do, right? Then you can do these kinds of what we call the construction 4.0, which is probably something which I will this is my area, which I will come to it in a moment. So what you can do is create what we call a digital twin of the entire construction, and then simulate various aspects of how to manage the construction and look at it in that sense. These models are not just 3D models, these are information models. So essentially, the model knows exactly what is in it. So what happens is I can query the model and ask it, okay, what would be the next maintenance schedule, and it will give it to me saying that the maintenance schedule for the elevator is this, the warranties of these kinds of equipment, like for example ACs and other things are due. So those are the things which you can now store in digital twins, and these are probably some of the cutting edge which you see in construction going on. Then if you do not want to stay in the lab, you can actually go to Himalayas also. Okay, so this is one of the research teams which is in the Himalayas. This is Professor Raj's team from the Hydro Remote Sensing lab of IIT Bombay, Civil Engineering. So he's from the Remote Sensing specialization of Civil Engineering. They actually track the glacier movements using remote sensing applications. So they actually make trips to all kinds of places in the world. So you have a wide range of areas where you can do research at Civil Engineering in IIT Bombay. And as you can see, much of this research is very interdisciplinary in nature. So you see that the lines are blurring. So you actually have a lot of components from different aspects of engineering coming together and thinking about solving these problems. Okay, so let's come to my work. So what you will do, for example, if you start working with me, I will show you a few applications of what we do at my lab. The first application, so let me just give you a small background. So I don't know how many of you actually use these kinds of technologies now, but if you imagine using such kind of technologies in present day world. Okay, unfortunately, some of our construction sites they use technologies which is almost similar to these, right? I mean, not literally but figuratively. Okay, so you still see a lot of paperwork, a lot of drawings which are still on paper, which people use to go and construct and communicate with each other, and that introduced lots of overhead and mistakes in construction. So the idea which we started off is to, can we reduce this entire thing and can we get into digital construction, right? So that's the idea. So we started off with this paradigms called building information modeling, which talks about how to store this huge amounts of information which is required for managing a construction project. And this paradigm, what we call the building information modeling, helps you to do that. And it will create what we call the digital twin of whatever you are constructing. And we go into what we call the automating construction paradigm. And this is also what we call the construction 4.0. So what are some of the things which we can do when we start looking at storing this information and analyzing this information to manage projects? The first thing what you can do, this is one of the project which one of our students have developed. What you can see is you can add a time dimension. Okay, so I hope you are able to see the video and you can simulate the entire construction sequence. And there is a lot of information in this model. So you can see the timeline which is running on the top left corner, then you see the different columns building up, etc. Now you can impose what's actually constructed on the site with what is planned. Okay, so you can impose the progress monitoring here. So the planning becomes much more easier. The visualization of the planning becomes much more easier, so that you can make decisions of when to procure material, etc. So it's an interesting application. We started off on that. Then we said, okay, let's do one more thing. We do not know what is built on the ground. Many a times what is built on the ground is very different from what is designed and planned and put in the drawing. So a cool application for that is to use the concept of what we call terrestrial lidar to actually get a nice point cloud of the entire structure. So this is what, if some of you come onto the campus, this is our PC Saxena auditorium. So what we did was we just went around and scanned this building. So what you see on the top left corner is a point cloud, which essentially means millions and millions of points, which are just X, Y, Z, and probably some information about light intensity and RGB values for it. Okay. So now the challenge is to process these millions of points to get a cool BIM model, which can then be used for various applications, right? For example, this models then can be used for understanding how sustainable the structure is, what's the energy usage of the structure is, right? What's the lighting load on the structure? Or you can also look at how vulnerable it is to seismic events like earthquakes or some kind of natural disasters. So you have now what we call an as-built BIM model, which can be imported from a point cloud, which you do by a laser scan, right? So applications are immense. Okay, so that's the challenge is, how do I process this millions and millions of points, assign planes to those points, attribute these points as belonging to a wall or a slab or a column or a beam. And it's quite intense in terms of computation. Okay, there is it's partially automated, but there are a lot of areas where there is a scope for research to automate these things. Okay, so you can start developing these things. Now, the cool thing about this is when you start developing BIM models, you can also automate things. Yeah, you can always also look at what we call the 3D printing technologies, etc., to print structures. Then you can have all kinds of weird shapes which you can start building. Okay, but that is again a technology which we will, which is a thrust area at IIT Bombay Civil Engineering, which some of you might be working on, right? And then there is this cool application which one of the BTech and an MTech student combinedly, some of helped by a PhD student developed. So this is what we call a serious game approach. Okay, so we developed this entire construction project using BIM, and then we have imported it into a gaming engine. So this is like a game which you play, okay, where various aspects of things are modeled, and actually you go and play the game and understand what's the safety problems on the site. So these kinds of technologies can then be used to train workers, and then can also be used to assess what's the kind of what is the kind of safety awareness these workers are. You can assess the workers as well, right? So that's one aspect. So let me just also understand, give you one more technology, which one more application which one of our this also students developed, and this went into publication as well. So this is something to use augmented reality to plan construction. And what these students have done is they've developed a cool augmented reality application where they focus on a building drawing, and then you see that the entire model comes up, right? And then what is cool about this is you can have 3 or 4 people looking at it from different angles using their mobile phones, and then you can actually look at different perspectives from different angles, right? And then you can actually move certain pieces on the drawing, and that automatically updates in your AR application, right? Now this application is being converted into mixed reality, where this will be now being housed on a HoloLens or some kind of lens, where you can actually wear the lens and then see what is happening on the drawing, right? The other interesting thing is, in the background we also have a very detailed information model, again using the BIM paradigm, and then we run a nice genetic algorithm, which is to optimize whatever planning you're doing, and then it gives you hints of whether whatever you're planning is all right or not. So it's kind of a business intelligence which we developed into it. Okay, so we are trying to convert this AR into a mixed reality application, and once you have a mixed reality application, the application of such a tool becomes quite interesting, because now what you can do is you can do away entirely with the drawings. You can just ask the construction worker to wear these kinds of lens, and then what you see is that worker can actually see what exactly to construct at what point in time. So you can integrate this with GIS and GPS systems to actually position the worker and then tell them what exactly they should build. So that eliminates entirely the problem of miscommunication of what to build, right? You'll be surprised that some of these structures are built inside out. Their orientations are different because people have misread these drawings. Okay, so we are trying to do something like that. Okay, so again, coming back to safety, we have developed this VR safety assessment module. So actually you can look at this virtual reality application. You can put up your VR box, and then you can actually go through the site and then understand what are the safety problems on the site, right? It's useful for VR, is useful for safety training, and it's also used for safety assessment. Okay, so if you come to my lab, sometimes you see these students in their own world, looking around and playing with these VR devices. Okay. Then I would like to come to the safety as the final application which I would like to show in this presentation. So this is a interesting application which we started developing, where we would like to monitor the safety using vision-based algorithms. Okay, so like some of the early presenters who showed face recognition, and also these kinds of vision-based algorithms for robots, etc. Similar kind of application we developed. This is using a vision-based deep learning neural network-based application to detect safety of construction workers. So what you see on the screen is a real-time screenshot of the application, where the application uses a feed like a CCTV camera or something on the side, and then it monitors these workers, and then it gives a real-time feedback to the construction planner or someone who's sitting at the dashboard on a computer, right? What it does is it gives you this idea that there is no helmet, there is no something. Okay, so this is a real-time tracking. The cool thing about, and this is developed by some of the BTechs and the PhD students in my lab. What you see, the thing is also, it's quite interesting, is that it has this real-time feedback. So for example, this is my students playing with the application, where one guy removed the helmet and gave it to the other guy, and then the algorithm in real time detects that there is a safety violation, right? So now it also has a small framework where it kind of compiles all these safety violations and then integrates it to the organizational process. Okay, so we use a convolutional neural network, a very deep learning network, which trained to do this. Okay, and this is also published recently by the student as well. Then we can do this intelligence to detect more. Okay, so this is again interesting application which I wanted to show you, because this started off so that Kumar S in that list is actually a BTech student, quite a intelligent one, I would say, smart person. He started off this project with me, then went to a university abroad for internship, continued this project, again came back, and then we have done this cool bit of technology which we can detect safety hazards on site. So this is in collaboration with the Hong Kong University, which we have done this, where you can detect potential danger zones when a construction worker comes in and give real-time feedback to managers on the site. Okay, so for example, here you see that ellipse or the red circle which you see here. What you see that is, this is exactly the danger zone, and you see that two workers here and here, they are actually coming into the danger zone. Okay, and the red says danger now, and then he says that if this guy moves into this area, then it becomes a danger. So that is color coded as well. So the idea is that these cranes actually dig the soil and move around, right? So the idea is is there a probability of hitting that construction worker when the crane when the excavator actually swings its arm? So that's the idea. Okay, so it's we have a nice bit of math which we do, and then we use a deep learning convolution neural network to actually do this. And the good part is this is done by a BTech student as part of this guy started off on third year and then went on to do it in as its BTech project as well. Okay, so it's kind of very interesting application. Apart from this, what you can also see is there are quite a bit of applications in terms of, for example, some of the students are working right now on natural language processing to develop smart contracts to detect what kind of disputes can happen on projects. There are also people who are starting to understand nano sensor based understanding of using IoT and IoE to understand progress monitoring and distress in structures. So there are quite a number of interesting areas which you can work on right at your BTech level, and you can start working it. So this is my research. If you're interested a little bit more, you can always contact me on email, and I'm open to questions as well.
Thank you, sir. Yeah, we have questions. So, Hiramani Mohan has asked, does BIM also simulate info on the types of materials to be used?
Yes, so that's the important thing, because this information model has quite a number of layers. So it's different from your traditional, CAD-based things, or let's say if you know these AutoCAD kind of applications where everything is just a line and a curve. Whereas a BIM-based model uses an object-oriented model where you have attributes. So you can actually say whether a wall is made of concrete or a brick or some other material. Not only that, you can build in a lot of other things as well. So you can always incorporate what's the thermoconductivity of that material is, what's the light reflectance of that material is, to actually do nice analysis of what would be the comfort level of the occupants, what would be the different kinds of material procurement which you can do. All those kinds of things can be incorporated. So it's a multi-dimensional information model which you actually have in building information model. Hope I answered the question.
Yeah, I guess that would answer the question. Let's move on to the next question. It is asked by Advait Risbad. His question is BIM relevant only to buildings or any large structure, say the construction of a jet engine?
So this BIM essentially works in the domain of construction. So you are looking at infrastructure projects like dams, roads, and all those things. For your jet engines and those kinds of models, you have an equivalent of that which is happening. So you have the computer-aided design and manufacture, which actually uses a similar kind of concept there as well. Okay, so but BIM is more or less in the construction domain.
Okay, I guess that would answer the question. Thank you, sir. It was a very insightful presentation.
Thank you. I will
Yes,
stop
we
my
should.
sharing now.
Yes, sir. Now, moving forward, next we have Professor Nishant Sharma from the Industrial Design Center School of Design. He has done research in the automotive design sector. He also has a rich industrial experience with companies like Bajaj Auto, Hero Global Design, and General Motors Tech Center. Handing over to Professor Nishant.
Thank you, Kriti, and thank you, Professor Atul, for giving this opportunity to talk to the bright minds today. I know I'm probably last in the session, but I will try to make it as interesting as possible. So
yeah, Nishant, we are sorry that you had to wait for some time. We are
No, that's
slightly
perfectly fine.
overshooting the time. Yeah, please. Please
as
go
long
ahead.
as students are fine with it, I'm perfectly fine.
Yeah. All right. Please go ahead.
Because the thing with coming late is that there are chances that either students will be put to sleep, or or
No.
or there are chances that they might just wake up even better. So
No, I'm sure they have been eagerly waiting for this talk. Yeah.
Sure. Yeah, thank you again. I'll give a little bit of twist to my talk, and I'll not just talk about research, I'll also talk about design, because since I represent IDC School of Design, and design and research are so much intertwined, and it's very difficult to really separate either of them. And I'm again very happy to be part of this very interesting Enthuse session, and I'm sure students will be able to make maximum out of all the talks that we had in the evening today. So IDC School of Design, just a very brief note on IDC School of Design. We just finished 50 years of our existence, and we were mainly Master of Design program. And in 2015, we also started Bachelor of Design. So the BDES students would have also joined this particular batch, and we also have PhD program, which also started late, but it was much before the Bachelor of Design program. So it's there for last 15 years. So in fact, in design, the PhD is a pretty new phenomena. So you won't find many PhDs across the globe. However, in India, there are many PhD researchers now. If I have to explain you what we do, and in a very nutshell and most amusing and interesting manner, just imagine that you're going through, you're seeing Jonathan Ive's sketchbook, and he's sketching something which is as beautiful as this one. And then there's a whole brigade of team that develops this thing. And I know, and you already know what thing I am talking about. You're talking about something, which is an Apple Watch. Now, how does it happen? And I just probably took 15 seconds to explain this, but it takes close to 2 years to 3 years to develop this. So if you know what people want, and if you know where technology is heading, if you know how to convert those desires and needs into a product, then you probably have understood how to design things. And that's precisely what we do in IDC School of Design. In IDC School of Design, we have 5 different disciplines, and as I showed in the slides, we started with industrial design, which is essentially to do with the product design. And then we have communication design. We have interaction design, everything which is related to HCI, designing apps, etc., and the service design. It all comes in the interaction design. And then we have animation design. And then we, of course, have something called mobility and vehicle design. And I represent mobility and vehicle design. I'm the coordinator of the program. So therefore, as I established already, that there is a lot of skill orientation, and there's a lot of sketching, and the students are taught how to sketch well, and of course they come with basic skills, and we work on those skills, and then you have to design things which are beautiful. At the end of the day, things that have to be manufactured and they have to be sold. That is the whole idea about designing products. So, and then of course you use CAD, and a lot of speakers have mentioned about CAD softwares and visualization softwares. The previous speaker also mentioned about AR and VR. So IDC is also very interesting melting pot of all the technologies. We use everything. We use all kinds of softwares, and we also use VR, AR sort of thing. In fact, we have a professor who is who has a specialty in AR and VR. So we do in this kind. We work a lot in this particular domain. Why am I rushing? Because I want you to firstly understand the context, and then I'll take you to a situation where I want you to think about it, a bit. So our students, they come up with products like these, which are desirable, which are sellable, and they are ready for the industry. So all the cars, all the products, all the things that you go and buy in the market, they are well thought of, and they are designed. They are designed and they are aimed for particular customers. So there's a hell lot of research that goes behind that. And then there is a lot of time that is spent in the design process of creating the products before it hits the market. And we also look at very futuristic products. This is the product that we imagined for Tata Motors. When, if it comes to autonomous cars, a couple of years back, our student was picked for the internship, and he was asked to imagine the autonomous car for the future, and looking at the context, looking at the Indian context, and this turned out to be an interesting image of the product, and we create visuals, we create such images. Now, having said all that, I am particularly interested in talking about something which is slightly different from what I just spoke. I wanted to explain about what we do in the IDC School of Design. Now I'm going to talk about what as a person, as a professor, what area I'm interested in. So for last couple of years, I've been working in the area of human-powered mobility, and I have a small studio, we makeshift studio, and we build bicycles, we build tricycles, and we also recently built something called Tricycle for Paraplegics, with some help from Ministry of Human Resources, MHRD. And in this image, you can clearly see that there is a juxtaposition of a tricycle which is ubiquitous. You will find everywhere in the country, wherever you are. I'm sure you would see that right inside tricycle. And there on the left hand side is something that we have designed as a response, to the requirements and the needs of the users who have lower limb disabilities. So just to give you some sort of initial understanding of the problem, and I'm sort of giving you these visuals so that you can also connect with it. I'm sure you would have seen these kinds of images a lot, but the reason I'm showing you these images is because as an engineer, as a designer, as an innovator, if you develop this habit of observing things more keenly, I think half of the problem is solved. So if you see the problems, and if you see what the person has done with the vehicle, whether that person is living on the vehicle or the vehicle is only for connecting him from A to B, and you will soon realize that there are many things which are happening on the vehicle, and the person is trying to personalize it, and is also carrying a lot of stuff along with him. When we did this research, we also found out that people actually live on these bicycles, on these tricycles, and especially in the big cities where they are homeless people, and they have this tricycle, and they're of course disabled. They carry huge amount of stuff around them, and that makes it of course very heavy. and also offers very little space for them to move around. So and they heavily depend on the donations that various companies do. Now, this is a very interesting visual, and I would like you to connect with this visual because when you do research and when you observe things, you will realize that they spend enormous amount of efforts in pushing the tricycle. They put a lot of efforts like this, but very rarely you will notice that the spine, the backbone has already got bent, because there's a lot of force which allows you to move on one side, and over a period of time, as an occupational hazard, it just tends to become go on to the left hand side. Now, this is irreversible because you can't get it, you can't set it right. So therefore, it seems that because of repetitive motions, there are certain things that you do harm. You bring a lot of harm to your body, and therefore it tends to become very irreversible. So how about designing things which are more suitable, for that particular use or for that particular context? So therefore, we spent enormous amount of time, and the reason I'm sharing this with the first year students is that you need to observe things. You need to very deeply, see things, and you should have curious eyes. And once you have the curious eyes, and once you start interacting with the users, I think lots of the lots of solutions will actually come from them. A small story, I mean, though very significant, but very small. This lady, for example, she fell from the tricycle when she was transferring from the wheelchair to the tricycle, the current tricycle. She fell down and there was nobody around. There was nobody to escort her. She was there on the floor for 2 hours. Now, this might surprise us that why should somebody be on the floor? Because if your lower limbs are not working, you will just stay on the floor. You can't rise even by a foot, or by half a foot if you have to use only your limbs, upper limbs. So therefore, it tends to become a very important aspect to observe things, interact, and find out what real problems are. And as we progressed, we found out that there are enormously large number of problems. And it also becomes very challenging in certain areas like these, because there is no specific precedent. So you don't have a project where, or you don't have any product from where you actually, which you make as a basis, and then you start from there. So you have something which is a tricycle, which is already, as I said, ubiquitous, lying, it's all over the country. And it is there in that particular architecture and situation for last 50 to 60 years, and nothing has changed. So it becomes even more responsible. There is a lot more responsibility on us to create things which are which show a lot more improvement. So the thing that we do in such cases, it's something called iterative design process, that we try out things which, we have certain ideas, and then we say that, well, maybe this will work, and then we start something with very basic so-called quick and dirty prototype. And if you see, these are the lab sort of prototypes, but we're trying to solve certain problems. And in the process, we also sort of concretize certain solutions, but then also keep certain solutions a little more abstract, because there's still no answers. And if you see these pictures on the right hand side, there are these two parallel bars which are triangulating the structure. Actually, that's a wrong thing to do, because if you have people who have lower limb disabilities, they can't move their legs at all through the tricycle. So you need to make sure that this is clear, and that became far more challenging for us to design the tricycles. Now, this is the first response of our design endeavor, and we created this tricycle. And if you see, there are these two handles, which will go like this, and it also maneuvers with that handle, and there are brakes and everything mounted on one. What it solved the problem of bent, over a period of time as an occupational hazard. You have this bent, the backbone, that you won't have such problem. And then with two hands, you are able to give initial, better initial torque, and then of course control the entire thing. With the previous one, you had the central member coming in the front, and then you could only use one hand to use it. So when you make such things, you also have to rely a lot on the local construction, local manufacturing setups. And I would like you to understand that there are a lot of small, what do you call that, cottage industries or the small scale industries where they make prototypes, and they also need some kind of development sort of projects. And we collaborated with few, and we tried to build the tricycle. And you will appreciate that since the tricycle was mainly for Mumbai, and Mumbai is also 4 months of rainfall, so it is natural to have a roof on it. And the moment you have the roof on it, you look at the canopy, and then you also start to collaborate with the auto rickshaw seat makers. The seat makers are the guys who also make seats for the auto rickshaws, but they also construct the canopy for the auto rickshaw. So there is the important thing here is that you also try and collaborate with people who already have certain kinds of skill sets and the knowledge. And with that, you can move slightly forward, and then you can also bring in your own ability to design. So it is your design, but you collaborate with a lot of people. So two words: one is observational ability, and second is collaboration. And I'm going to utter a few words which I think may be very useful to you slowly. And of course, as I said, it's an iterative process, and there are lots of problems. There is. If somebody is able to make something which is absolutely right at the first go itself, and I think that's pretty genius of him. But generally, that doesn't happen. You have to spend enormous amount of time making, breaking, reiterating. So there were a lot of issues in this. I won't go into the details of what the issues were, but definitely that pushed us to not stop but try out things better. So we made a structure. We made a new structure, and that was far more stronger and more stable. And of course, the idea was that the entire thing should exhibit the idea of confidence. As I said, that we work with people a lot, and the initial feedback that we got, from a lot of people, and also a lot of students who were in IIT Bombay and who had disabilities. In government institutions, they give tricycle for free to all the needy. But what happens? A lot of students, they don't use it. And it's very surprising. They don't use it because they don't feel connected with it. They feel that this will put them down, and people will start looking at them as disabled people, and that's something that they don't want to associate with. And many of these tricycles just lie, in the campus all over, all the government institutions. Even in IIT Bombay, there are a couple of these tricycles which are just lying there. Now, we wanted to create something which gives them an idea of confidence, and we worked on the branding of it. And then we wanted to make it more attractive, nicer, and of course solves all the problems that I have already mentioned, to the extent that even if somebody has to leave the crutches inside it, you should be able to do that, and there's a little pocket in which the crutches will go, and the ease of transfer, and even the smaller details, like if you have to reverse your tricycle and park it, and there are these orange rings on it, just like wheelchairs, you can just fine tune it and take them backwards and park them. Of course, the tricycle also was fully covered. As I mentioned, that's Mumbai. Never, and the third word which I want to use here is the context. Always design for the context. Whatever is the context. So if the context demands it to be low cost, and for the situation like Mumbai, for situation like India, design for it. If you leave these, if you leave the context, and if you think something which is going to be more futuristic and more expensive, I think the solution will not work. So in order to make the solution work, you have to work within the context. And that's the idea. And if you, this is not the proper engineering exploded view, but it's a design exploded view. The idea was that it should just be packaged inside a box. Anybody who places an order, we just we ship this out to the person, and with the help of local, cycle guy, you can just quickly assemble and make the tricycle. Of course, we didn't stop here. There was some issues with the structural with the structure, and collaborated again with mechanical engineering department. We found some problems and we solved those, and again made another prototype, because you have to keep doing it till you are happy with it. And the fourth thing which I want to talk about here is that never go to the final user, the real user, till you are happy with it. So this is the first time when we actually went to the real users. So these are the students who have lower limb disabilities or any other mobility disability. And we went to them with this tricycle once we were happy with it. And they gave enormous feedback, and we fine-tuned it, and we worked on it again. And this is the final image of the product that we developed. Some more views of it. And this is the final prototype, and this was the time for us to now go out of the IIT and go to real field, real world outside. And we went to Paraplegic Foundation in Mumbai, and I just want to show you some of the videos. So these people, they were so excited that they started, as soon as we arrived there, they started using it. And of course, the idea was not that it's not always true that your expectations of people being happy with the product would always be met, and there are chances that people will be happy for sure, because obviously your intent was nicer and you wanted to make things better. But then you should also be ready to, you should be ready to take up even the negative feedback, which will be very useful. So all the negative feedback that came to us, we worked hard towards it and ensured that all the negative feedback was actually, used in developing this product better. So yeah, so at this time, this gentleman, he's saying that, I'm using this kind of mechanism for the first time. So I'm feeling little pain here on my, lower arms. But then he also says that, since I'm doing it for the first time, so maybe a couple of days later, I think I should be fine. So we did very, elaborate user testing. And no design is good design unless you test it, because there's no point. If you make designs only for, just for the sake of it and don't test it, what's the point? So we tested it, and there was very, very good feedback. However, we also got not so good feedback from the women riders, because they felt, and I think that's a design problem, they said that the overall size of it looks too large and they find it very uncomfortable. So we are still working on that. But in general, in terms of its drivability, I think they were pretty good. They were pretty happy with that. So now some of these slides I wanted to show you because this will help enthuse you. I mean, if I may borrow this word from this enthuse as a session, that we would love to have such kinds of tricycles for children, and if any of you are interested in doing that, more than welcome. And I'm very sure, I'm not reading the chat, but I'm sure you may have ideas as to why you're not making electric, because this is one question that I keep getting, and to answer that, we did the electric version, we did the pedal assist also. But the cost, as I said, it has to be designed for the context, and the context demanded things to be low cost. And most of these people are heavily dependent on the donations of the tricycles, which can come from the government, or it can also come from the corporate social responsibility. So there's a process. I mean, I can explain you that process of on some other occasion, but generally you should have a certificate of disability, and then the government, based on the funds and the tricycles available, they will donate the tricycles. So making it electric and making it pedal assist electric tricycle makes it 3 to 4 times more expensive. So that was a big bottleneck. Of course, if you ask me what is the best solution, there is no doubt, there's no iota of doubt in my mind that it has to be electric, it has to be pedal assist. There has to be some energy which should be used. However, in absence of that, and because of the fact that it is very expensive, the human powered tricycle still will be able to answer some of the problems that we have already listed down. So this is the pedal assist, and many of you probably are not aware of IIT. This is hillside, and of course there's a positive slope on the road, and the rider is very easily riding it and driving it because of pedaling. I mean, of course, the electric motor kicks in here and is able to do it. But as I said, this is just an attempt to integrate our electric. So we wanted to ensure that our tricycle is not just human powered ready, but it is also ready to even have the electric motor or pedal assist. So that's so these are the few things which I thought I'll share with you. Of course, it's a longish video, but yeah, I mean, it's a similar thing. And of course, we would also like to have this kind of tricycle. And when we presented it various places like TechFest and all, a lot of elderly people came to us and they said, we don't use bicycles these days, and of course our legs, we have arthritis and some other issues. So maybe something which is hand pedal can be a very good equipment, so to say, a mobile equipment for exercising or giving some strength to our body. Fair enough, and we understood that. And I'm not saying that this is we designed that particularly for that, but I think this can also be adapted. But to be honest with you, we did not design for purely for elderly, for strengthening their upper body muscles. The area that I'm also very interested in, and I'm sure some of you might get interested, is that there are enormously large number of para-athletes in our country, and they're devoid of good wheelchairs and tricycles. And the reason I'm saying this is that this lady, she actually represents India as a parathlete, and she got in touch with us, and she wanted to use our tricycle for very long adventure ride. However, I said that we did not design that particularly for the adventure. But when we collaborated with her, we found out that there is an enormously large opportunity available for all of us to work in this area. The tricycle that you're seeing here, this is imported one, and costs close to 6 to 7 lakhs of rupees. Okay. However, India is a country where the bicycle manufacturing is not expensive. Just to give you some figure, that we make close to 1.2 to 1.3 lakhs bicycles a day, sometimes 1 lakh or 1.2 lakhs. I mean, with the lockdown, I think it would have gone down. But some companies make 40 to 50,000 bicycles a day. So obviously our cost of manufacturing is way too low. But I'm just saying that it is possible to create very high quality, lightweight, tricycles and wheelchairs for para-athletes. This is one area we want to venture into. We have not gone in yet, but I just thought I'll share with you in case some of you are interested in doing in this area, interested in working in this area. And of course, we have presented it in various TechFest, and media was kind enough to cover it. Just to say that we developed protos and we have tested. Electric version has also been tried, and there's some sort of conversation going on whether to you know whether to start as an entrepreneurship venture or should be given out to people to manufacture it. So that's something that's currently on. Yeah, so that's a little complicated subject, but that's the update on this particular tricycle project. Yes, so I think I've taken way too much time, but thank you so much. In case you're interested in getting in touch with me, you can email me. Sorry, I've not put my email ID here, but you can just look for my name in IDC website, and you can find my email ID. Thank you so much.
Thank you, sir. It was a very insightful presentation. So we can take question. We can take one question. Rohit Mandhyan has asked this question.
Yes.
Can it be developed into auto type vehicle that can give them an earnings of their own too?
Yes. When you say auto type, you mean that they should be able to ferry people. Is it what you're trying to say?
Yes, sir.
Okay.
There are many
Yeah,
questions
good question.
related to this.
Good question. In fact, you saw that video where the gentleman is riding and is testing. So this guy, he actually, interestingly, if you see this tricycle, can you see my screen right now, Kriti?
Yes, sir.
Yeah. So there, this orange portion at the back side, this is actually a luggage space. So you can buy stuff. If you're coming home, you can buy veggies, fruits, etc., and you can put that. And this is a lockable space. Okay. So when we showed this to this man, and he used it, and he said, "You know what, sir? Can you do one thing?" I said, "Yes. Tell me what." He says, "Can you just remove the luggage box and actually put a seat there?" I said, "Why you want a seat?" He says that every day I actually take my child to the school, and he sits next to me. It's little inconvenient because there's not enough space in the front seat. So if you can create a small seat at the back, I'll be very happy to take him from home to his school. And that gave us an idea, I'm trying to sort of connect with what this student just asked. And I think there is some need in the people to have one more seat to it. And I agree there has to be some way to allow this person to earn bread, with this vehicle. So we have been thinking about it to connect this with the system of, some sort of work. In fact, you'll be very surprised to know that there are people in the Paraplegic Foundation, and if you're aware of Mumbai, so Sion to Borivali is pretty long distance, pretty long, and these people, they actually deliver some of the products that they make in the Sion Paraplegic Foundation, and they actually go all the way to Borivali and they hand pedal, and then they come back. So they're very hardworking people, and then they already are doing such kinds of jobs and works. So definitely this will really and point well taken. I think that will really help them earn self-respect and also be able to earn some money for themselves and their family. Sure.
Thank you, sir. I guess that answers this question well. So I guess we should move forward due to time constraints.
Sure.
So it was a really insightful presentation.
Yeah.
Students enjoyed this. Yeah.
So much.
So thank you everyone for waiting so much. So now the most asked question that I was getting in the chat box, that how do we get projects, which department should we go, and so many queries. I could totally relate when I was in first year. I had same questions. So to answer those questions, Shruti will give you a small presentation prepared by the Student Council regarding what all research opportunities are there. Yes,
Yeah,
sir.
Kriti, if I can take a minute or so.
Yes, sir. Yes, sir. Sure.
Yeah, so before Shruti, I'm sorry, but I just wanted to take this opportunity to thank all the professors, like particularly Nishant, who waited for a long time. Actually, and we are sorry for that he was made to wait. But I take this opportunity to all the professors who had kindly agreed to our invitation or our request to address these young students about their respective research work. And I can see, Professor Jaya is still around. Professor Nishant is of course here. I can see Venkata. So thanks for your patience. And you people have really made this event hugely successful. And once again, thank you very much.
Thank you so much, Professor Atul. I think it was the pleasure was all ours. You know,
no, I think your last talk had actually brought out the meaning of enthuse. It was an apt relation to whatever the spirit of this event is. Thanks a lot, Nishant, once again.
Thank you so much. Thank you.
Yeah. Shruti, now take over, please.
Yes, sir, sure. I'll just share my screen. Is my screen visible? Hello?
Yeah, Shruti?
Is my screen visible?
It says it is, you have started to share the content. Not yet.
Okay, maybe some internet issue or something. Is it visible now?
No, we are getting the same.
Shruti, if you can just switch off your video, that might improve the bandwidth.
Acha, yes, sure.
Yeah.
We can see it now, Shruti.
Yeah, we can see it. Yeah, thanks for that. Right.
Okay, yeah. Okay, so hello everyone. I'm Shruti Agrawal, a second year undergraduate from the physics department and an academic coordinator from EnPoWER. So a lot of you have been asking the question that if you're interested in research, how to approach a professor, how to take up a project under a professor. So I'll be telling you about that. So research is obviously, just a second, my laptop. Yeah, so research is obviously one of the most important aspects of IIT Bombay, and we have various opportunities for all of you. IIT Bombay has 16 departments, 19 centers, 4 interdisciplinary programs, and a school of management. There are various high technology labs conducting world-class research. In whatever field you are interested in, IIT Bombay has opportunities in that. A lot of you have been asking that does department matter? For example, if you are from a specific department, can you conduct research or explore research in another department? So yeah, that's definitely possible. Not just the departments that have BTech, but also other departments like we saw in the previous presentation, design, biotechnology, management. In all these fields, research opportunities are available. And if you're interested in that, you can definitely approach professors from those departments and conduct research under them. So how to do so? So the two most major approaches available are, firstly, is with the help of the events conducted by us, that is EnPoWER and the Undergraduate Academic Council. And secondly, you can definitely directly approach a professor. So firstly, I'll tell you how we at EnPoWER help you to take up projects. EnPoWER stands for Engineering-Oriented Promotion of Work Experience and Research. And our major goal is to bridge the gap between professors and students and help you guys take up projects. We conduct some of the research programs. Two of the most major ones are SERP and ISERP. SERP stands for Summer Undergraduate Research Program, and as the name suggests, it is conducted during the summers when you have a break from your semester and you have ample of time to pursue projects. Second one is ISERP. It is similar to SERP, except for the fact that it's conducted during the semester. So for these programs, we have a centralized portal, project allocation portal. We upload projects on the portal, which are sorted on the basis of departments. You can go to that portal and apply for projects. So this is how the SERP, ISERP portals look like. As you can see, there are projects from various departments, multiple projects from all of these departments. And according to your interest, you can register for any of these projects. And a very simple selection procedure is conducted by the professors, and then you can take a project under them. So here is a QR code for the ISERP portal in case you want to check it out. I'm going to pause for a few seconds. So moving on, you can definitely directly approach the professors. All of the professors of our institute are really approachable and helpful and always ready to guide us undergraduates. So the first step would be to find your interest. If you're interested in, say, a particular arena of aerospace engineering, you can go to the department website, and there you'd see a list of all of the faculty members along with their research interests as well as their contact details. So whichever professor you feel that your interests align with them, you can contact them. You can contact them via email, or if we are in the institute, you can definitely ask for an appointment in their office. You can discuss with them over the idea that you have, or even if you're not very sure about what you want to work upon, but you are interested in the research interest and want to read more about it, you can mail the professor and schedule a meeting with them and discuss about the project. Again, as I said earlier, the professors are really helpful and always ready to guide us. Even if you want some reading material or you want to discuss your ideas with them, they'd be very happy to. So we have created a novice's guide to take up projects under the professor. You can find this pinned on the EnPoWER Facebook page. It gives you a brief introduction on how you can approach the professor in case you have any queries. We at EnPoWER also organize curious community discussions and student interest groups. The main aim of these groups is to connect like-minded people and help you discuss your ideas, your doubts with other people, maybe seniors who have more experience than you and would be happy to guide you. This is again a QR code of the Curious Community group on Facebook. You can scan this, it will take you to the group and you can join it. We conduct various discussions and talks on a lot of topics. You can also suggest us topics that you'd like to hear talks on, and we'd be happy to conduct those. So moving on. To help you further on this, we have various department research coordinators from respective departments. If you want to connect from, say, some seniors from your department that you think would be able to guide you on a particular research interest or a particular idea that you have, you can approach any of these department research coordinators. And again, like I said earlier, you are not restricted to your own department when it comes to research. You can definitely, approach other professors as well as seniors from other departments if you're interested in that. So this is the team EnPoWER. You can contact any of us if you have any queries on how to take up projects, or if you, like I said, we conduct various programs, SERP, ISERP, which are specially formulated to help you take a project. If you have any queries, you can contact us. And finally, these are the QR codes of our Facebook and Instagram page. All of the details regarding our events are posted on these. So follow these to stay updated. Also, like many of you were asking for the slides of the presentations of today's orientation, we'd once take a permission from the professors and we'd upload the slides on these social media handles. So You can check those out there. So I think with this, we come to the end of this orientation. I'd like to thank all the professors who took out their time and enlighten all of us on their research interests. I'd also like to thank Atul sir for making this event possible.
Yeah, thanks a lot, Shruti. I think it is you people who have actually made this event, and I take this opportunity to thank all the students volunteers, Ayush, you, Kriti, n number of students volunteers who have actually contributed towards the successful conduct of this event. And once again, a lot of thanks to you as well as to all the professors who had kindly agreed to be a part of this event. Of course, in my opinion, it has been quite effective. We had so many interesting talks regarding ranging from various fundamental aspects to real life applications. So this has been possible because of the efforts that have been put in by the students body. Thanks a lot. Thank you very much. And special thanks to all the young entrants, the first year students who would be joining soon, for staying with us. It is almost now we are approaching midnight, but I can see that you people are still connected. So thanks a lot for this, and we are looking forward to welcome you all in physical terms as and when you come back to IIT campus. All right, so please take care, and I think we will close the session here. Kriti or Shruti, if you can formally announce the closure of the session.
Yeah, sir. So again, I'd like to thank all of the professors, Atul sir, and of course, all of you guys for making this session possible. We really hope that it helped you and it enthused you for the amazing research that has been conducted in our institute. You can approach any of these professors, any of us volunteers, part of Team EnPoWER, if you have any queries or if you want to talk to us further about the research opportunities at IIT Bombay. So again, thank you to everyone, and we'd like to close the session here now.